the Alfred P. Sloan Foundation.
We've done pretty mysteries. For thousands of years, we've been trying to unlock the mysteries of how the universe works. And we've done pretty well, coming up with a set of laws that describes the clear and certain motion of galaxies and stars and planets. But now we know, at a fundamental level, things are a lot more fuzzy, because we've discovered a revolutionary new set of laws that have completely transformed our picture of the universe. From outer space to the heart of New York City, to the microscopic realm, our view of the world has shifted, thanks to these strange, mysterious laws that are redefining our understanding of reality. They are the laws of quantum mechanics. Quantum mechanics rules over every atom and tiny particle in every piece of matter, in stars and planets, in rocks and buildings, and in you and me. We don't notice the strangeness of quantum mechanics in everyday life, but it's always there if you know where to look. You just have to change your perspective and get down to the tiniest of scales, to the level of atoms and the particles inside them. Down at the quantum level, the laws that govern this tiny realm appear completely different from the familiar laws that govern big, everyday objects. And once you catch a glimpse of them, you never look at the world in quite the same way. It's almost impossible to picture how weird things can get down at the smallest of scales. But what if you could visit a place like this, where the quantum laws were obvious, where people and objects behave like tiny atoms and particles? You'd be in for quite a show. Here, objects do things that seem crazy. I mean, in the quantum world, there's a sense in which things don't like to be tied down to just one location, or to follow just one path. It's almost as if things were in more than one place at a time. And what I do here can have an immediate effect somewhere else, even if there's no one there. And here's one of the strangest things of all. If people behave like the particles inside the atom, then most of the time, you wouldn't know exactly where they were. Instead, they could be almost anywhere until you look for them. Hey, I'm gonna have what he's having. So, why do we believe these bizarre laws? Well, for over 75 years, we've been using them to make predictions for how atoms and particles should behave. And in experiment after experiment, the quantum laws have always been right.
It's the best theory we have.
There are literally billions of pieces of confirming evidence for quantum mechanics.
It has passed so many tests of so many bizarre predictions.
There's no disagreement between quantum mechanics and any experiment that's ever been done.
The quantum laws become most obvious when you get down to tiny scales like atoms. But consider this. I'm made of atoms. So are you. So is everything else we see in the world around us. So it must be the case that these weird quantum laws are not just telling us about small things. They're telling us about reality. So how did we discover them? These strange laws that seem to contradict much of what we thought we knew about the universe. Not long ago, we thought we had it pretty much figured out. The rules that govern how planets orbit the sun, how a ball arcs through the sky, how ripples move across the surface of a pond. These laws were all spelled out in a series of equations called classical mechanics, and they allowed us to predict the behavior of things with certainty. It all seemed to be making perfect sense, until about 100 years ago, when scientists were struggling to explain some unusual properties of light. In particular, the kind of light that glowed from gases when they were heated in a glass tube. When scientists observed this light through a prism, they saw something they'd never expected.
If you heated up some gas and looked at it through a prism, it formed lines. Not the continuous spectrum that you see projected by a piece of cut glass on your table, but very distinct lines.
It wouldn't give out a smeared, kind of complete rainbow of light. It would give out sort of pencil beams of light at very specific colors.
And it was something of a mystery how to understand what was going on.
An explanation for the mysterious lines of color would come from a band of radical scientists who, at the beginning of the 20th century, were grappling with the fundamental nature of the physical world. And some of the most startling insights came from the mind of Niels Bohr, a physicist who loved to discuss new ideas for ping pong. Bohr was convinced that the solution to the mystery lay at the heart of matter, in the structure of the atom. He thought that atoms resembled tiny solar systems, with even tinier particles called electrons orbiting around a nucleus, much the way the planets orbit around the sun. But Bohr proposed that unlike the solar system, electrons could not move in just any orbit. Instead, only certain orbits were allowed.
And he had a really surprising and completely counter-physical idea, which was that there were definite states, fixed orbits that these electrons could have, and only those orbits.
Bohr said that when an atom was heated, its electrons would become agitated and leap from one fixed orbit to another. Each downward leap would emit energy in the form of light in very specific wavelengths, and that's why atoms produce very specific colors. This is where we get the phrase quantum leap.
If it weren't for the quantum leap, you would have this smear of color coming out from an atom as it got excited or de-excited. But that's not what we see in the laboratory. You see very sharp reds and very sharp greens. It's the quantum leap that's the origin and the author of that sharp color.
What made the quantum leap so surprising was that the electron goes directly from here to there, seemingly without moving through the space in between. It was as if Mars suddenly popped from its own orbit out to Jupiter. Bohr argued that the quantum leap arises from a fundamental and fundamentally weird property of electrons and atoms, that their energy comes in discrete chunks that cannot be subdivided, specific minimum quantities called quanta. And that's why there are only discrete, specific orbits that electrons can occupy.
An electron had to be here or there and simply nowhere in between. And that's like nothing we experience in everyday life.
Think of your daily life. When you eat food, you think your food is quantized? Do you think that you have to take a certain amount of minimum food? Food is not quantized. But the energy of electrons in an atom are quantized. That is very mysterious, why that is.
As mysterious as it might be for tiny particles in an atom to act this way, the evidence quickly mounted showing that Bohr was right. In more and more experiments, electrons followed a different set of rules than planets or ping pong balls. Bohr's discovery was a game changer. And with this new picture of the atom, Bohr and his colleagues found themselves on a collision course with the accepted laws of physics. The quantum leap was just the beginning. Soon Bohr's radical views would bring him head-to-head with one of the greatest physicists in history. Albert Einstein was not afraid of new ideas. But during the 1920s, the world of quantum mechanics began to veer in a direction Einstein did not want to go. A direction that sharply diverged from the absolute definitive predictions that were the hallmark of classical physics.
If you asked Einstein or other physicists at the time what it was that distinguished physics from all kind of flaky speculation, they would have said it's that we can predict things with certainty. And quantum mechanics seemed to pull the rug out from under that.
One test in particular, which would come to be known as the double-slit experiment, exposed quantum mysteries like no other. If you're looking for a description of reality based on certainty, your expectations would be shattered. We can get a pretty good feel for the double-slit experiment and how dramatically it alters our picture of reality by carrying out a similar experiment, not on the scale of tiny particles, but on the scale of more ordinary objects, like those you'd find here in a bowling alley. But first, I need to make a couple of adjustments to the lane. You'd expect that if I roll a few of these balls down the lane, they'll either be stopped by the barrier or pass through one or the other slit and hit the screen at the back.
No, that's fine. What am I gonna have up here now?
And in fact, that's just what happens. Those balls that make it through always hit the screen directly behind either the left slit or the right slit. The double slit experiment was much like this, except instead of bowling balls, you use electrons, which are billions of times smaller. You can picture them like this. Let's see what happens if I throw a bunch of these balls. When electrons are hurled at the two slits, something very different happens on the other side. Instead of hitting just two areas, the electrons land all over the detector screen, creating a pattern of stripes, including some right between the two slits, the very place you'd think would be blocked. So, what's going on? Well, to physicists, even in the 1920s, this pattern could mean only one thing. Waves. Waves do all kinds of interesting things. Things that bowling balls would never do. They can split. They can combine. If I sent a wave of water through the double slits, it would split in two, and then the two sets of waves would intersect. Their peaks and valleys would combine, getting bigger in some places, smaller in others, and sometimes they cancel each other out. With the height of the water corresponding to brightness on the screen, the peaks and valleys would create a series of stripes in what's known as an interference pattern. So, how could electrons, which are particles, form that pattern? How could a single electron end up in places a wave would go?
Particles are particles, waves are waves. How can a particle be a wave? Unless you give up the idea that it's a particle and think, aha, this thing that I thought was a particle was actually a wave. A wave in an ocean? That's not a particle. The ocean is made out of particles, but the waves in the ocean are not particles. And rocks are not waves. Rocks are rocks. So a rock is an example of a particle. An ocean wave is an example of an ocean wave. And now somebody's telling you a rock is like an ocean wave. What?
Back in the 1920s, when a version of this experiment was first done, scientists struggled to understand this wavy behavior. Some wondered if a single electron, while in motion, might spread out into a wave. And the physicist Erwin Schrödinger came up with an equation that seemed to describe it.
Schrödinger thought that this wave was a description of an extended electron, that somehow an electron got smeared out and it was no longer a point, but was like a mush.
There was a lot of argument about exactly what this represented.
Finally, a physicist named Max Born came up with a new and revolutionary idea for what the wave equation described. Born said the wave is not a smeared out electron or anything else previously encountered in science. Instead, he declared it's something that's really peculiar, a probability wave. That is, Born argued that the size of the wave at any location predicts the likelihood of the electron being found there.
Where the wave is big, that's not where most of the electron is. That's where the electron is most likely to be.
And that's just very strange, right? So the electron on its own seems to be a jumble of possibilities.
You're not allowed to ask, where is the electron right now? You are allowed to ask, if I look for the electron in this little particular part of space, what is the likelihood I will find it there? I mean, that bugs anyone, anytime.
As weird as it sounds, this new way of describing how particles like electrons move is actually right. When I throw a single electron, I can never predict where it will land. But if I use Schrodinger's equation to find the electron's probability wave, I can predict with great certainty that if I throw enough electrons, then say 33.1% would end up here, 7.9% would end up there, and so on. These kinds of predictions have been confirmed again and again by experiments. And so the equations of quantum mechanics turn out to be amazingly accurate and precise, so long as you can accept that it's all about probability. If you think that probability means you're reduced to guessing, the casinos of Las Vegas are ready to prove you wrong. Try your hand at any one of these games of chance, and you can see the power of probability. Let's say I place a $20 bet on number 29 here at the roulette table. The house doesn't know whether I'll win on this spin, or the next, or the next.
1.
But it does know the probability that I'll win. In this game, it's 1 in 38.
21. 29.
So, even though I may win now and then, in the long run, the house always takes in more than it loses. The point is, the house doesn't have to know the outcome of any single card game, roll of the dice, or spin of the roulette wheel. Casinos can still be confident that over the course of thousands of spins, deals, and rolls, they will win. And they can predict with exquisite accuracy exactly how often. According to quantum mechanics, the world itself is a game of chance much like this. All the matter in the universe is made of atoms and subatomic particles that are ruled by probability, not certainty.
At base, nature is described by the inherently probabilistic theory. And that is highly counterintuitive and something people would find difficult to accept.
One person who found it difficult was Einstein. Einstein did not believe that the fundamental nature of reality at the deepest level was determined by chance.
This is what Einstein could not accept. Einstein said, God does not know that we couldn't with certainty say this happens or that happens.
But a lot of other physicists weren't so put off by probability, because the equations of quantum mechanics gave them the power to predict the behavior of groups of atoms and tiny particles with astounding precision. Before long, that power would lead to some very big inventions. Lasers, transistors, the integrated circuit, the entire field of electronics. If
went on strike, every single machine that we have in the US almost would stop functioning.
The equations of quantum mechanics would help engineers design microscopic switches that direct the flow of tiny electrons and control virtually every one of today's computers, digital cameras, and telephones.
Did it really
All the devices that we live on, diodes, transistors, just to form the basis of information technology, the basis of daily life in all sorts of ways. They work. And why do they work? They work because of quantum mechanics.
Okay, maybe I'm just...
I'm tempted to say that without quantum mechanics, we'd be back in the Dark Ages. I guess more accurately, without quantum mechanics, we'd be back in the 19th century. Steam engines, telegraph signals.
Quantum mechanics is the most successful theory that we physicists have ever discovered. And yet we're still arguing about what it means, what it tells us about the nature of reality.
In spite of all its triumphs, quantum mechanics remains deeply mysterious. It makes all this stuff run, but we still haven't answered basic questions raised by Albert Einstein all the way back in the 1920s and 30s. Questions involving probability and measurement, the act of observation. For Niels Bohr, measurement changes everything. He believed that before you measure or observe a particle, characteristics are uncertain. For example, an electron in the double-slit experiment. Before the detector at the back pinpoints its location, it could be almost anywhere with a whole range of possibilities. Till the moment you observe it. And only at that point will the location's uncertainty disappear. According to Bohr's approach to quantum mechanics, when you measure a particle, the act of measurement forces the particle to relinquish all of the possible places it could have been and select one definite location where you find it. The act of measurement is what forces the particle to make that choice. Niels Bohr accepted that the nature of reality was inherently fuzzy, but not Einstein. He believed in certainty, not just when something is measured or looked at, all the time. As Einstein said, I like to think the moon is there, even when I'm not looking at it.
That's what Einstein was so upset about. Do we really think the reality of the universe rests on whether or not we happen to open our eyes? That's just bizarre.
Einstein was convinced something was missing from quantum theory. Something that would describe all the detailed features of particles, like their locations, even when you're not looking at them. But at the time, few physicists shared his concern.
Einstein just thought it was giving up on the job of the physicist. It wasn't bad physics per se, it just was totally incomplete.
That's Einstein's defense. Quantum mechanics is not incorrect insofar as it goes, but it's incomplete. It doesn't capture all the things that can be said or predicted with certainty.
Despite Einstein's arguments, Niels Bohr remained unmoved. When Einstein repeated that God was not so dumb, Bohr responded, "Stop telling God what to do." But in 1935, Einstein thought he finally found the Achilles heel of quantum mechanics. Something so strange, so counter to all logical views of the universe, he thought it held the key to proving the theory was incomplete.
The most bizarre, the most absurd, the most crazy, the most ridiculous prediction that quantum mechanics made is entanglement.
Entanglement is a theoretical prediction that comes from the equations of quantum mechanics. Two particles can become entangled if they're close together and their properties are linked. Remarkably, quantum mechanics says that even if you separated those particles, sending them in opposite directions, they could remain entangled, inextricably connected. To understand how profoundly weird this is, consider a property of electrons called spin.
Yes, electrons
Unlike a spinning top, an electron spin, as with other quantum qualities, is generally completely fuzzy and uncertain until the moment you measure it. When you do, you'll find it's either spinning clockwise or counterclockwise. It's kind of like this wheel. When it stops turning, one landed red, the other is guaranteed to land on blue. And vice versa. Now, since the wheels are not connected, that's suspicious enough. But the quantum mechanics embraced by Niels Bohr and his colleagues went even further, predicting that if one of the pair were far away, even on the moon, with no wires or transmitters connecting them, still, if you look at one and find red, the other is sure to be blue. In other words, if you measured a particle here, not only would you affect it, but your measurement would also affect its entangled partner, no matter how distant. For Einstein, that kind of weird long-range connection between spinning wheels or particles was so ludicrous, he called it spooky. Spooky action at a distance.
Yeah. What's surprising is that when you make a measurement of one particle, you affect the state of the other particle. You change its state.
There's no forces or pulleys or, telephone wires. There's nothing connecting those things, right? How could my choice to act here have anything to do with what happens over there?
So there's no way they can communicate with each other. So it is completely bizarre.
Bizarre.
Einstein just could not accept that entanglement worked this way, convincing himself that only the math was weird, not reality. He agreed that entangled particles could exist, but he thought that there was a simpler explanation for why they were linked that did not involve a mysterious long-distance connection. Instead, he insisted that entangled particles were more like a pair of gloves. Imagine someone separates the two gloves, putting each in a case. Then that person delivers one of those cases to me. The other case, to Antarctica. Before I look inside my left hand or right hand glove, and when I open my case, I find a left hand glove. Then after there's nothing mysterious about this. Obviously, by looking inside the case, I've not affected either glove. This case has always had a left-hand glove, and the one in Antarctica has always had a right-hand glove. That was set from the moment the gloves were separated and packed away. Now, Einstein thought that exactly the same idea applies to entangled particles. Whatever configuration the electrons are in must have been fully determined from the moment that they flew apart. So, who was right? Bohr, who championed the equations that said that particles were like spinning wheels that could immediately link their random results even across great distances, or Einstein, who believed there was no spooky connection, but instead everything was decided well before you looked?
I do not feel like filling this entire room.
Well, the big challenge in figuring out who is right, Bohr or Einstein, is that Einstein is saying a particle, say, has a definite spin before you measure it. How do you check that, you say to Einstein? He says, well, measure it, and you'll find the definite spin. Bohr would say, but it's the act of measurement that brought that spin to a definite state. No one knew how to resolve the problem. So the whole question came to be considered philosophy, not science. In 1955, Einstein died, still convinced that quantum mechanics offered, at best, an incomplete picture of reality. In 1967, at Columbia University, Einstein's mission to challenge quantum mechanics was taken up by an unlikely recruit. John Clauser was on the verge of earning a PhD in astrophysics, the only thing standing in his way was his grade in quantum mechanics.
When I was still a graduate student, try as I might, I could not understand quantum mechanics.
Nobody really knows.
Clauser was wondering if Einstein might be right when he made a life-altering discovery. It was an obscure paper by a little-known Irish physicist named John Bell. Amazingly, Bell seemed to have found a way to break the deadlock between Einstein and Bohr and show once and for all who was right about the universe.
I was convinced the quantum mechanical view was probably wrong.
Reading the paper, Clauser saw that Bell had discovered how to tell if entangled particles were really communicating through spooky action, like matching spinning wheels, or if there was nothing spooky at all, and the particles were already set in their ways, like a pair of gloves. What's more, with some clever mathematics, Bell showed that if spooky action were not at work, then quantum mechanics wasn't merely incomplete, as Einstein thought. It was wrong.
I came to the conclusion that, my God, this is one of the most profound results I've ever seen.
Bell was a theorist, but his paper showed that the question could be decided if you could build a machine that created and compared many pairs of entangled particles.
Bell turned the question into an experimental question.
It wasn't just going to be about philosophy or trading pieces of paper.
And the experiment that he envisioned could be done.
You could really set up an actual experiment to force the issue.
Clauser set about constructing a machine that would finally settle the debate.
Now, I was just this punk graduate student at the time. This really seemed like, wow. There's always the slim chance that you will find a result that will shake the world.
Clauser's machine could measure thousands of pairs of entangled particles and compare their spins in many different directions. As the results started coming in, Clauser was surprised and not happy.
I kept asking myself, what have I done wrong? What mistakes have I made in this?
Clauser repeated his experiments, and soon French physicist Alain Aspect developed a more sophisticated test. With significantly more definitive results, Aspect removed virtually all lingering doubt. Clauser's and Aspect's results are truly shocking. They prove that the math of quantum physics is right. Entanglement is real. Quantum particles can be linked across space. Measuring one thing can in fact instantly affect its distant partner, as if the space between them didn't even exist. The one thing that Einstein thought was impossible, spooky action at a distance, actually...
Again, very sad that I'm not able to throw in quantum mechanics because I still have, and to this day, great difficulty with understanding.
That is the most difficult thing of quantum mechanics. It is impossible to even comprehend. Don't even ask me why. Don't ask me which you're going to how it works, because it's an illegal question. All we can say is that is apparently the way the world ticks.
So if we accept that the world really does tick in this bizarre way, could we ever harness the long-distance spooky action of entanglement to do something useful? Well, one dream has been to somehow transport people and things from one place to another without crossing the space in between. In other words, teleportation. Star Trek has always made beaming or teleporting look pretty convenient. It seems like pure science fiction, but could entanglement make it possible? Remarkably, tests are already underway here on the Canary Islands off the coast of Africa.
We do the experiments here on the Canary Islands because you have two observatories, and after all, it's a nice environment.
Anton Zeilinger is a long way from teleporting himself or any other human. But he is trying to use quantum entanglement to teleport tiny individual particles, in this case photons, particles of light. He starts by generating a pair of entangled photons in the lab on the island of La Palma. One entangled photon stays on La Palma, while the other is sent by laser to the island of Tenerife, 89 miles away. Now Zeilinger brings the third photon, the one he wants to teleport, and has it interact with the entangled photon on La Palma. The team studies the interaction, comparing the quantum states of the two particles. Here's the amazing part. Because of spooky action, the team is able to use that comparison to transform the entangled photon on the distant island into an identical copy of that third photon. It's as if the third photon has teleported across the sea without traversing the space between the islands.
Sort of extract the information carried by the original and make a new original data.
Using this technique, Zeilinger has successfully teleported dozens of particles. But could this go even further? Since we're made of particles, could this process make human teleportation possible one day?
Welcome to New York City.
Let's say I want to get to Paris for a quick lunch. Well, in theory, entanglement might someday make that possible. Here's what I'd need. A chamber of particles here in New York that's entangled with another chamber of particles in Paris.
Paris? Who's in Paris?
Right this way, Mr. Green.
I would step into a pod that acts sort of like a scanner or a fax machine. While the device scans the huge number of particles in my body, more particles than there are stars in the observable universe, it's jointly scanning the particles in the other chamber, and it creates a list that compares the quantum states of the two sets of particles. And here's where entanglement comes in. Because of spooky action at a distance, that list also reveals how the original state of my particle is related to the state of the particles in Paris.
Paris?
Next, the operator sends that list to Paris. There, they use the data to reconstruct the exact quantum state of every single one of my particles. And a new me materializes. It's not that the particles travel to Paris. That entanglement allows my quantum state to be extracted in New York and reconstituted in Paris.
Oh, in Paris.
Down to the last particle.
Bonjour, Monsieur Green.
There. So, here I am in Paris, an exact replica of myself. And I'd better be, because measuring the quantum state of all my particles in New York has destroyed my original image.
It is absolutely powerful in the quantum process. And, you know, that does make you a little anxious. I guess you would just end up being a lump of neutrons, protons, and electrons. You wouldn't look too good.
Now, we are a long way from human teleportation today, but the possibility raises a question. Is the Brian Green who arrives in Paris really me? Well, there should be no difference between the old me in New York and the new me here in Paris. And the reason is that, according to quantum mechanics, it's not the physical particles that make me me. It's the information those particles contain. That information has been teleported exactly for all the trillions of particles that make up my body.
It is a very deep philosophical question whether what arrives at the receiving station is the original or not. My position is that by original we mean something which has all the properties of the original. And if this is the case, then it is the original.
I wouldn't step into that machine.
Whether or not human teleportation ever becomes a reality, the fuzzy uncertainty of quantum mechanics has all sorts of other potential applications. Here at MIT, Seth Lloyd is one of many researchers trying to harness quantum mechanics in powerful new ways.
Quantum mechanics is weird. That's just the way it is. So, you know, life is dealing us weird lemons. Can we make some weird lemonade from this?
Lloyd's weird lemonade comes in the form of a quantum computer.
These are the guts of a quantum computer.
This golden brass contraption might not look anything like it, but at its heart, it speaks the same language. Binary code. A computer language spelled out in zeros and ones, called bits.
So the smallest chunk of information is a bit. And what a computer does is bust up the information in small steps and then puts them really rapidly.
This quantum computer speaks in bits, but unlike a conventional bit, which at any moment can be either 0 or 1, a quantum bit is much more flexible.
You know, something here can be a bit. Here is 0, there is 1. That's a bit of information. So if you can have something that's here and there at the same time, then you have a quantum bit or qubit.
Just as an electron can be a fuzzy mixture of spinning clockwise and counterclockwise, a quantum bit can be a fuzzy mixture of being a 0 and a 1. And so a qubit can multitask.
That means you can do computations in ways that our classical brains could not have dreamed of.
In theory, quantum bits could be made from anything that acts in a quantum way, like an electron or an atom. The qubits at the heart of this computer are tiny superconducting circuits built with nanotechnology that can run in 2 directions at once. Since quantum bits are so good at multitasking, if we can figure out how to get qubits to work together to solve problems, our computing power could explode exponentially. To get a feel for why quantum computing would be so powerful, imagine being trapped in the middle of a hedge maze. What you'd want is to find the way out as fast as possible. The problem is there are so many options. And I just have to try them out, one at a time. That means I'm going to hit lots of dead ends, go down lots of blind alleys, and make lots of wrong turns before I finally get lucky and find the exit. And that's pretty much how today's computers solve problems. Though they do it very quickly, they only carry out one task at a time, just like I can only investigate one path at a time in the maze. But if I could try all the possibilities at once, it would be a different story. And that's kind of how quantum computing works. Since particles can, in a sense, be in many places at once, the computer could investigate a huge number of paths or solutions at the same time and find the correct one in a snap.
That'd be really bad for passwords.
Now, a maze like this only has a limited number of routes to explore, so a conventional computer could find the way out pretty quickly. But imagine a problem with millions or billions of variables, like predicting the weather far in advance. We might be able to forecast natural disasters like earthquakes or tornadoes. Solving that kind of problem right now would be impossible because it would take a ridiculously huge computer. But a quantum computer could get the job done with just a few hundred atoms. And so the brain of that computer, it would be smaller than a grain of sand. There's no doubt we're getting better and better at harnessing the power of the quantum world. And who knows where that could take us. But we can't forget that at the heart of this theory, which has given us so much, there is still a gaping hole. All the weirdness down at the quantum level, at the scale of atoms and particles, where does the weirdness go? Why do things in the quantum world hover in a state of uncertainty, seemingly being partly here and partly there, with so many possibilities, while you and I, who after all are made of atoms and particles, seem to always be stuck in a single, definite state? We are always either here or there. Niels Bohr offered no real explanation for why all the weird fuzziness of the quantum world seems to vanish as things increase in size. As powerful and active quantum mechanics has proven to be, scientists are still struggling to figure this out. Some believe that there's some detail missing in the equations of quantum mechanics. And so, even though there are multiple possibilities in the tiny world, the missing details would adjust the numbers on our way up from atoms to objects in the big world, so that it would become clear that all but one of those possibilities disappear, resulting in a single certain outcome. Others believe that all of the possibilities that exist in the quantum world may never be broken. Instead, each and every possible outcome actually happens in other universes, parallel to our own. It's a mind-blowing idea, but reality could go beyond the one universe we all see and be constantly branching off, creating new, alternative worlds where every possibility. This is the frontier of quantum mechanics, and no one knows where it will lead.
The very fact that our reality is much grander than we thought, much more strange and mysterious than we thought, is to me also very beautiful and honest.
The beauty of science is that it allows you to learn things which go beyond your wildest dreams. And quantum mechanics is the epitome of that.
You're never really the same again.
As strange as quantum mechanics may be, what's now clear is that there's no boundary between the worlds of the tiny and the big. Instead, these laws apply everywhere, just as the weird pieces are most apparent when things are small. And so the discovery of quantum mechanics reveals a reality, our reality, that's both shocking and thrilling, bringing us that much closer to fully understanding the fabric of the cosmos.
Major funding for NOVA is provided by David H. Koch and
Discovering New Knowledge. HHMI.
and by the Corporation for Public Broadcasting, and by contributions to your PBS station from viewers like you. Thank you.
Why black hole environments are a lot more complicated.
Showing up on the first page of Google might not be the best for everyone.
Jason, does that...
Cole, he's my miracle child. Okay. So how does your miracle...
Black holes are one of the most mind-boggling aspects of space. For a start, they aren't actually objects. They are the result of the extreme warping of space-time. And because of this warping, some really weird stuff starts to go on around them that will change your perspective of the way the universe operates around you. Some of it is so strange that perhaps you won't believe it was true were it not for the solid math that back up their existence and properties, and the increasing evidence that the math is correct through observations in our own universe.
I'm Alex McColgan and you're watching Astrum, and in this video we will be exploring the unexplorable. Join me on this journey as we attempt to understand the weird science of how a black hole forms, what goes on around them, and explore what might actually allow for an escape from the most inescapable prisons in existence. I hope by the end of this video to have earned your like and subscription.
Black holes come in a variety of sizes. The smallest observed black hole is around 3.8 solar masses. On the other side of the scale, we find black holes that have been in existence since almost the start of the universe, black holes weighing billions of solar masses. These behemoths are not only massive, but also huge. They would easily fit in the entire solar system within the diameter of their event horizon. Black holes being created today are the final stage in the life cycles of particularly massive stars. When such a star is born, it is essentially balancing under the weight of two forces. The first is gravity, pushing its mass towards its center. Down in the depths of the star, hydrogen atoms are crushed against other hydrogen atoms with such force that they combine to form a denser element, helium. This new atomic structure actually needs less energy than it did when it was two individual, separate hydrogen atoms, so the extra energy left over gets released. This released energy is the second force. It radiates back out from the center of the star as heat and light, counteracting the force of gravity pushing in. In this state, the star will remain relatively stable until such a time as the reaction begins to stop as it runs out of its hydrogen fuel. If the star is massive enough, once the hydrogen begins to run low, the star will combine the newly formed helium into even denser materials like carbon, neon, and eventually oxygen and silicon. But then it begins fusing iron. The issue with iron is that it doesn't save any energy in its new form, so has no spare energy to release. It just sits in the core of the star, growing larger. With no energy pushing back against gravity, very quickly the scale tips. The energy of this collapse is astounding, but the force is dependent on the original mass of the star. Like a hammer striking on an anvil, the mass of the star rushes down to meet the core with such force that the rebound of that blow is what we call a supernova. Matter and energy are blasted out across the universe from the crackback in one of the largest explosions possible, which produces elements even heavier than iron, all the way up to uranium. And what is left of the star? Well, it depends. If the mass of the star, and thus the force of the blow, was too low, what remains is a neutron star, a small ball of matter at most around 25 kilometers in diameter, and yet so densely packed with mass that it equals 1 million Earths. But if the mass and thus force was big enough, physics as we know it breaks down, and we are left with a black hole. When you see an image of a black hole, the black sphere you are looking at is not actually the black hole itself. Scientists theorize a black hole's true form is probably even smaller and denser than a neutron star. In fact, it is likely infinitely small and infinitely dense, a singularity emitting forces that warp time and space itself. However, we don't know, and the reason we don't know is because of something called the event horizon. All objects with mass exert gravity. We've known this since the days of Newton. However, when Einstein came along in 1915 with his theory of general relativity, a contemporary of his called Karl Schwarzschild reasoned from it that there could exist objects that were so massive they could create enough gravity that light itself could not escape. And if even massless light photons couldn't get out, nothing could. When you look at a picture of a black hole, you're not seeing the black hole itself. You are seeing the event horizon around it, the demarcation line where gravity has become so powerful that light can no longer leave. there is nothing but darkness. Now, its effect on space is one thing, but black holes also impact another aspect of the universe, time itself. You see, according to Einstein, space and time are inseparably connected, and mass warps space-time. With the singularity's infinite point of mass, it stretches space-time so much that the event horizon also marks the point where time stops. Within the event horizon, space and time basically cease to exist, a place where there is no where or when. This produces an interesting phenomenon to an outside observer watching matter fall into a black hole. From their perspective, as matter approaches the black hole, it will slow down until just before the event horizon, where it will stop altogether. You won't ever see it cross the event horizon. There will be no satisfying absorption. Instead, the matter will gradually dim until you can't see it anymore. When first theorized, astronomers and physicists were uncertain if black holes were actually real. It was only 40 years later that the first evidence of a black hole was recorded. In 1964, using newly developed X-ray satellites, scientists noticed an object in the constellation Cygnus that seemed to be emitting a large amount of X-rays. Strangely enough though, scientists could not see the object itself. It surprised them because if it was a star, it ought to emit visible light as well as X-ray radiation. Scientists called this object Cygnus X1. In 1970, as telescopes advanced, they noticed that whatever Cygnus X1 was, it had formed a binary orbit with a star in its system, and this helped scientists calculate its mass. They discovered that this invisible object was 15 times more massive than the Sun. As the densest neutron star had an upper limit of 3 times the mass of the Sun, scientists realized that this was most likely the first ever discovered black hole. Since then, we have discovered many black holes. Massive ones seem to exist at the center of galaxies, and we've even managed to take photos of some, dark blots against the swirling ring of matter that surround them and fall into them, their accretion disk. This is how black holes can still be detected through X-rays. While black holes can't emit visible electromagnetic radiation themselves, the X-rays that come from them actually originate from their accretion disks, where infalling matter gets heated to millions of degrees Celsius through intense friction. Black holes with no infalling matter are basically invisible, with no bright accretion disk to spot. Exploring black holes is still a developing field in physics, and there is still much to learn. From what we have learned so far, you may wonder if a black hole could ever stop being a black hole, or will it grow forever until there is no matter or radiation left in the universe? It would seem so.
We're the doers, the ones who choose a different kind of classroom, the ones.
However, in 1974, in his paper entitled Black Hole Explosions, physicist Stephen Hawking postulated that there was actually a way that energy, and thus mass, could leave a black hole. But to understand why, we have to get into some extremely weird theory. We need to examine some principles of quantum mechanics. But first, let me ask you a difficult question. What is nothing? Imagine for a second a patch of space with nothing inside of it. There's no atoms of space dust, not even radiation passing through it. As near as can be seen, nothing exists within it. And yet, is there really, truly nothing there? Something fundamental exists here, and we can tell that this is the case when a beam of light travels through it. If you are familiar with the properties of light, you will know that light is actually waves of electrical and magnetic charge that are constantly propagating with each other forwards in a straight line. However, let's take a look at that word wave. A wave in the sea is the propagation of energy moving through the water. If you were to look at an individual particle of water, it's not really going anywhere except in a circle. And yet, because it passes energy to the atoms next to it, energy travels towards the shore in a constant motion that goes all the way to the beach. Similarly, a sound wave moves by passing energy between air particles, with each particle only moving a tiny bit, becoming energized and then passing that energy to the next particle in line. But in our vacuum of space, where there is nothing in it, where our photon of light is traveling in waves, have you ever stopped to wonder what exactly is waving? This hints at a fundamental something that exists even in nothing, a fabric that makes up all of reality itself. Quantum physicists call this something a quantum field. Quantum fields are tough to wrap your head around, but they are inescapably important when it comes to understanding the fate of a black hole. So, how do quantum fields and exploding black holes tie together? Going back to Hawking's paper, Hawking hypothesized that black holes would release energy slowly over time in initially tiny quantities. As energy and mass were two expressions of the same thing according to Einstein's famous E equals mc squared equation, this inevitably resulted in a reduction in the black hole's mass. However, as the black hole shrinks, the rate of energy release would speed up, getting faster and faster, until in the very last moments of the black hole's life, it would release a burst of energy that was truly gargantuan in its scale, before vanishing entirely. But how can this be true? It is well known that an event horizon is inescapable, so how could radiation ever leave it and eventually cause such a black hole explosion? The answer is a strange one and relies on unintuitive ideas of quantum theory that completely go against our day-to-day experience. But if it's true, I hope you're prepared for the universe to be a whole lot stranger than you thought. But to begin understanding Hawking's theory, we need to understand the idea of quantum fields. Remember, light moves like a wave through even a completely empty patch of space, which reveals that there must be something existing even in nothing, or else light wouldn't be able to wave it. Scientists call this fundamental fabric of reality a quantum field. In fact, they believe that there are several quantum fields, all overlapping each other, and all covering every single patch of the universe, be it past, present, or future. Quantum field defines a particular type of something. One field might define all of the electrons in existence, while another may define quarks that make up an atom. Where nothing can be found, the quantum field is relatively quiet. Think of it like a guitar string that hasn't been strummed, or a graph that has a zero value. But wherever in time and space mass or energy can be found, the quantum field is resonating at that point. And when the resonance reaches a certain threshold or quantity, the universe expresses that as, say, an electron or a photon. It's important to note that in this theory, the resonance is not just reacting to a piece of matter, it is the matter. An electron is nothing more than a resonating section of the quantum field that defines electrons. This is true for all energy and all matter too. According to Einstein, energy and matter are two sides of the same coin after all. All the universe you see around you is resonating quantum fields and nothing more. In this way, the theory portrays all of the universe as a song being played on these fields, which I think is quite a beautiful image, if nothing else. But why does this matter? Why is it important to define the universe in this way? Well, due to an idea of quantum physics called Heisenberg's uncertainty principle, sometimes the strings of the universe start strumming themselves. Without going too deeply into this aspect of quantum physics, essentially, when we're looking at really tiny objects on the atomic scale, it becomes impossible to know too much about them. You cannot know both the location and the direction of travel of an electron, for instance. Because it is so small, as soon as you try to figure out the location of an electron, it bounces off whatever you are trying to use to measure it, so you can no longer be sure of its direction of travel. If you know its direction, according to this principle, you can't know its location. This is not just because our methods of measuring aren't good enough, but because of some fundamental laws about the nature of the universe itself. According to Heisenberg's uncertainty principle, you cannot know everything about particles on a subatomic level. But when you apply this principle to quantum fields, it gets weird. Quantum fields fluctuate everywhere, and by Heisenberg's uncertainty principle, particle and antiparticle pairs can actually pop in and out of existence. The how and why get complicated, but basically the universe allows it as long as they only exist for a very short period of time, as ruled by uncertainty relations. You might think this can't possibly be a thing. Matter does not just pop into existence. We would have surely noticed this by now. However, in an experiment done by Hendrik Casimir, evidence was found that suggests that this might actually happen. Casimir took 2 plates of conductive metal and placed them close enough together so that only certain sizes of smaller virtual particles could pop into existence between them. This limited the number of such particles that could pop into existence. But because all types of particles could pop into existence on the outside of the plates, this meant that there was a difference in pressure exerted on the 2 sides of each plate. Theoretically, the larger pressure by the number of virtual particles on the outside of the plate should push the 2 plates together, and in the test, this proved to be the case. You might think that particles appearing out of nowhere seems to defy the laws of conservation of matter. You would be right. So, to balance the scales, whenever a virtual particle appears, a second particle also pops into existence to pair up with the first particle. But while one of the particles is matter, the other is antimatter. A 1 and a -1 on our bar chart, thus keeping things overall at 0. The universe is happy. And on top of that, these fluctuations in the quantum field quickly crash into each other and annihilate each other, removing them both from existence again, so we don't only have to worry about them. As a side note, there is a theory that antimatter is simply matter that is moving in the opposite direction through time, but that's a level of weirdness that we don't need to get into here. The important part is that the quantum fields are constantly resonating and constantly cancelling each other out. This is why, for the most part, empty space is empty. However, what would happen if you stopped only some of those fields resonating? And that's where black holes come in. Black holes act a bit like putting your thumb on the guitar string of the universe. Due to their event horizons, certain resonances in the quantum fields are dampened down while others are not. Hawking imagines sketching a line through time in a patch of space where a black hole was born. He imagined a quantum field that resonated along this line, stretching from before the existence of the black hole into the future after it. Before the birth of a black hole, all is normal. Quantum fields are all resonating freely and can cancel each other out. However, the emergence of the black hole's event horizon changed the curvature of space, and outside it, Hawking realized that certain pulses were now missing their opposite numbers. As he looked at the math, he realized not everything was being cancelled out anymore after the black hole had formed. Indeed, outside the event horizon, traveling away from the black hole, he found resonances that perfectly matched the shape of thermal radiation flying away into space. Radiation is energy, and energy cannot form from nothing. As the black hole was creating this radiation, the black hole would have to pay the price. Every piece of Hawking radiation would thus coincide with an equal amount of energy lost from the black hole, which in time would reduce it down to nothing. If it exists, Hawking radiation is kind of like money spontaneously appearing outside of a bank, while inside the bank, the money in the vault vanishes. It's also extremely difficult to prove, as Hawking predicted this radiation would be colder than the background cosmic radiation that fills the universe, and would have a wavelength as long as the black hole's event horizon itself. As some black holes have event horizons the size of solar systems, we have no way of detecting this kind of radiation. We'd only really see it once the universe had gone cold and dead, so there was nothing else to get in the way, which would probably mean we weren't around anymore to do the detecting. However, in spite of the objections to it, the math behind Hawking radiation seems to be sound, and scientists have recently taken steps to proving it in the lab. In the Technion Israel Institute of Technology, researchers looking into Hawking radiation came up with an idea to get around the difficulty of measuring a real-life black hole. They did this by creating an analog, a sonic black hole, which would mimic the properties of a real one. They relied on the fact that sound moves much slower than light, so it's much easier to create a medium that moves faster than sound. When it moves, any sound waves traveling in the same direction as it can never quite escape it. Interestingly, Hawking's math worked for these sonic black holes just as well as it did for gravity-based ones, and so Hawking radiation ought to be detected from it. After repeating the experiment 97,000 times over 124 days of continuous experimentation, the researchers detected multiple instances of Hawking radiation and saw that it matched Hawking's predictions of how his radiation might behave. Although this does not prove that Hawking radiation is definitely real for actual black holes too, the fact that Hawking's math worked for this sonic analog is a strong implication that he might be onto something. Hawking radiation might just be real. So, if you fell into a black hole, could you ever escape? Probably not. However, if you waited until almost the end of the universe, the black hole may just radiate Hawking radiation until the mass and energy that made up your existence was completely removed from inside the event horizon. Does that count as escaping? That's probably not so appealing to you. Probably best just not to go in. And that's not the only weird thing about black holes. Their existence implies something quite worrying about our own reality. When you're walking on a beach and you make a footprint in the sand, there is no question in your mind that it is your foot that caused the footprint. The order of causality is quite clear here, so much so that it seems laughable to even need to assert it. You made the footprint didn't make you. But what if it did? What if I told you that on the cosmological scale, the fundamental relationship between foot and footprint might be a little more blurred than you would intuitively think? And shockingly, due to the nature of black holes and Hawking radiation, there is some evidence that this might just be the case. But to begin with, we're going to need to look at a principle called relativity. But no, not that relativity. Galilean relativity. First described by Galileo Galilei in 1632, the idea of this form of relativity is that there is no difference between being completely still and moving at continuous speed. Imagine there are two rooms, one on the ship and another on land. Both are soundproof and have no windows. Imagine the sea is calm, so there's no rocking at all. The only difference between the two rooms is that one is moving and the other is not. Can you tell the difference between the two from the inside? You might think that you'd be able to sense movement, but this is not the case. For instance, right now, you are careening through space at 110,000 kilometers per hour due to the Earth's movement around the sun. And if you are sitting down at home while watching it, it's likely you would have said you weren't moving at all.
This is Mary. This is your dog living their best life with real deboned meats.
In fact, Galileo realized that there was no test that could be done to tell the difference between the two scenarios. He even found that if you dropped a ball in the ship, from your perspective, it would look like it fell straight down, even if, from the perspective of a person on land, it would look like it was falling diagonally. Galileo realized that if you remove all frames of reference, say by being in space, there is no way of telling if a planet is moving towards you or you are moving towards a planet. According to relativity, both are equally valid interpretations. You might have noticed this yourself if you ever looked out of the window on a train just as another train suddenly passed by, quickly overtaking you. Although both trains are going forwards, the other train is going faster than yours, and because you no longer have a frame of reference to compare your motion to, it might look as if you are suddenly going backwards. Einstein took this idea further with his equivalence principle. Here he took the idea of two rooms again, but this time he was making an observation about gravity. If you were inside a windowless room floating in the vacuum of space, and someone started accelerating your room in the up direction, say by strapping a rocket to the bottom of it, if the rocket accelerated at just the right speed, then it would feel identical to if you were standing in a room on the surface of Earth. In other words, there is no way to tell the difference between the acceleration caused by gravity and the acceleration caused by a rocket, assuming you couldn't stop the rocket shaking you with all its rumbling, of course. Both these principles rely on the idea of inertia. that objects do not like to move if simply left on their own, and do not like to stop moving once they have started. Anytime you want a mass to do something different to what it is doing, a new force must be applied, otherwise it will remain inert. But why would it feel to the man in the room with the rocket as if he were under the effects of gravity? Or perhaps a better question, why would it feel to us on Earth as if we were being accelerated upwards by the effects of the rocket? The Earth is not expanding in all directions at once, pushing us with it, surely. While this is true, Einstein realized that the two felt similar because they both were the same thing, a form of acceleration. However, there is another form of acceleration that better explains how gravity works than simply applying a force to an object to push it like a rocket does. Consider this spinning fairground ride. If you have ever been on such a ride, you will know the power of changing direction as a form of acceleration. When you stand against the wall of the ride, as it gets up to speed, you feel a constant force pressing you against the wall, even when the ride spins at a constant speed. This is because your mass is trying to move in a straight line at each point in the ride, but the curvature of the ride is forcing you to alter your direction. The battle between your inertia trying not to change what you're doing and the wall trying to alter your direction of travel manifest as the force you feel. And as far as acceleration is concerned, there's not much difference between the Earth beneath you accelerating you up and you trying to accelerate down. Einstein realized that this form of acceleration caused by a curving path, was the best explanation for gravity. He came up with a theory that matter and energy cause a warping in the space around it, kind of like how a ball might bend the surface of a taut rubber sheet it was placed on. The larger the mass, the greater the curvature. And once space was curved, any object trying to travel through it would be deflected by that curve. In the words of physicist John Wheeler, space tells matter how to move. Matter tells space how to curve. For small masses, this curve in space would be very slight, but in dense masses, this curvature could get so great that it would be impossible for an object that got too close to it to escape it. These are the conditions we find near a black hole with its event horizon. So, going back to our very first analogy of the footprint of the foot, if a black hole is the foot, the curvature of space around it is the footprint. It's interesting to see all this in action and to understand how Einstein came to conclusions which would have been almost universally validated by scientists even 100 years on. But there's nothing particularly weird about any of this. Understanding the exact mechanism behind it doesn't make it any stranger. The black hole tells space how to curve, and once curved, any object moving near it is told how to move. Nothing here is outside our expectations based on day-to-day observations. But when we start to look at Hawking radiation, something very strange happens. The most important thing to bear in mind about it for the purposes of our current video is that it is non-local. This means that it does not appear from the black hole itself, but appears from the area of space around it. To be clear, I do not mean beyond the singularity of the black hole, but still within the black sphere. That's hard to define anyway. Space as we know it doesn't exist there. Remember, the black ball you see here is simply the demarcation point between inescapable curvature and escapable curvature, the event horizon. I do not even mean right up against the event horizon, although that is sometimes how this theory is portrayed. People sometimes speak of two particles popping into existence right up against the event horizon, with the antimatter particle just inside it so it falls in, while the normal particle is just outside and so escapes. This is not what is happening. Instead, the region of space this radiation can pop into existence is several times the size of the event horizon, a distance up to billions of kilometers away. And when the largest black holes we have can comfortably fit multiple solar systems side by side inside of their event horizon, the idea that a photon of radiation can pop into existence this distance again outside the event horizon is crazy. It happens even in a place where there is literally nothing there. So in short, it is not so much that Hawking radiation is coming from the black hole directly. Instead, it is coming into existence from the curvature of space that the black hole is creating, and can happen quite far away from the black hole itself. But if that is true, then things work completely opposite to what we might expect, as you will see in a moment. Consider what happens in this order. As energy leaves the curvature of space, the curvature lessens because of something known as the conservation of energy. And as this reduction of curvature happens, the black hole then shrinks. This is crazy. This is like the footprint getting smaller, and so the foot shrinks accordingly. It feels very wrong. Things can't possibly work that way. And yet Einstein hinted that such a thing might indeed be possible. In one of his equations, he stated that the curvature of space-time was proportional to the mass energy of an object. But proportional is not causation. There's no presupposition that one causes the other in this relationship. We are comfortable with the idea of changing mass and so changing curvature, but it works just as well if you go the other way and change the curvature to change the mass. If this is true, then it hints at a universe where mass is simply a projection caused by space curvature. When you shine a light at an object, say your hand, and it makes a shadow on the wall, the shadow is a projection caused by the existence of your hand interacting with the light. Normally in this analogy, you might be forgiven for believing that we are the hand. It is our mass that creates the curvature of space around us. And yet, do we really know that it doesn't work the other way around? Are we simply projections, shadows on the wall of the universe being brought into life by something more fundamental going on in the curvature of space-time? And yet, we're going around thinking that we are the thing that's real. We don't really know. Given that all you know is the reality you experience, it would be difficult for you to be able to tell the difference between the two scenarios. But if relativity has taught us anything, it's that if there's no way of telling the difference between the two situations, then we can't completely dismiss that we're in one and not the other. Either that, or the two might be more linked than we thought. Of course, obviously, this is all just a theory. There is no hard proof that Hawking radiation is even a real thing, although there have been some experiments that hint that it might be. But this is just something interesting to think about. And even if it does prove to be the case that reality is a projection, it's not going to affect your day very much. You will still think, feel, and that's more than enough reason for you to go about doing what you can be doing. But it is an example of how, when we start to examine the very fundamental building blocks of reality by exploring the weird warping effects of black holes, it can cause us to challenge assumptions about our very nature. After all, when you're asking the question, am I real? And the answer is, it's not certain, that's more than a little concerning. Either way, black holes affect our reality and they affect our universe. And not just because they suck everything within their reach into them and give nothing back. They are the end, the final destruction of the universe. And yet, what if I said to you that they might actually prove to be our salvation? Black holes might provide the answer to traveling faster than the speed of light and solving the energy crisis in ways we couldn't have even imagined until recently. And as by now I have come to expect, they do so by messing with the fabric of reality itself and by completely countering our expectations of physics. Perhaps we have been thinking about black holes all wrong.
Be right back, I need water.
But to understand how a black hole ignores the usual limitations on faster than light travel and does so in a way that you can benefit from it without having to go inside a black hole's event horizon, and how it produces near limitless energy at the same time, then we are going to have to understand more about the features of black holes than we've covered so far. It's actually quite difficult to say much about a black hole's features at all. Precisely because of the event horizon, we cannot see what the inside of a black hole looks like. In fact, there are only 3 things we can say about black holes with any degree of certainty. They have mass, they have charge, and they have angular momentum. You might wonder how we know these things about black holes, given that no light can leave them to tell us about them. The key to these three characteristics is that all three of them represent aspects of the black hole that can be felt outside the black hole's event horizon. Charge, for instance, works the same way around a black hole as it does around any other charged object. That is to say, if a black hole is charged, then it will attract objects that have different charge to it and repel objects that share its charge. Think of it like a giant magnet, pushing and pulling on the universe around it. Scientists can track objects that approach a black hole, and by seeing how quickly certain objects known to have a charge move towards it, scientists can predict the charge of the black hole itself. Interplaying with this is mass. The mass of a black hole can also be felt outside the sphere of the event horizon. In fact, it is the main creator of the event horizon in the first place. This is because mass creates gravity and does so in a linear fashion in accordance with the same principles you might find in Gauss's law, a theorem about electromagnetism, albeit with a gravitational analog. So, it's possible too to calculate the mass of an object by seeing how far away objects are before they start to accelerate towards it, and how quickly they accelerate. Although obviously, you need to factor in charge at the same time, or your results might get skewed. Finally, angular momentum, or spin. It is possible to detect the spin of a large mass object, and we are going to dive into the how in just a bit. For now, let's just accept it as a given and recognize that black holes are certainly very high mass objects. There are varying sizes of black holes in existence. The smallest, known as micro black holes, have a mass that's comparable to that of our moon, or 7.35 times 10 to the power 22 kilograms. They fit all this into a space that's just 0.2 millimeters in diameter, which is incredible. It really gives you a sense of how dense a black hole can be, something thinner in size than a human hair, packing the mass of the moon. And that's just the smallest ones. Stellar black holes have a mass equal to 10 times our sun, and have a diameter equal to 60 kilometers. Intermediate black holes are the mass of 1,000 suns, and fit all of that into a diameter of 2,000 kilometers, which is still much smaller than the Earth. It is the largest black holes that really dwarf us, with masses between 100,000 to 10 billion times the mass of the Sun, and sizes ranging from 0.001 to 400 astronomical units, an astronomical unit being the distance from the Earth to the Sun. But other than those three features, there are in theory no other differences between them. If you put two black holes in the same room and made sure they had the same mass, charge and spin, it would be impossible to tell them apart. However, these three features are enough to have some interesting effects on the area of space outside a black hole. Traveling inside a black hole is impossible. Space and time break down past the event horizon, but we think we know a few things that must exist inside one. Beating in the heart of a black hole, there is thought to lie the singularity. In truth, this actually is the black hole. When we were discussing diameters earlier, that is just the diameter of the event horizon. Again, we are not certain what a black hole actually looks like, because light can never escape it. In a space that is infinitely small, there is a point where all the mass of the black hole is packed, so that it is infinitely dense. For the simplest models of black holes, the ones that do not spin, this is a single point. In a rotating black hole, this is more like a little spinning ring. Otherwise, it would be difficult to define spin for a point that has no volume. Our current physics get very strange around such a black hole. If ideal paths are traveled around this point, it becomes mathematically possible to do some very strange things, like meet up with your own past. This has some disturbing implications for causality and gets into time travel paradoxes like the grandfather paradox. So that probably only shows for certain that our ideas about singularities are not quite right yet. Because the singularity is so small, it'll take the successful merging of quantum theory and general relativity theory to properly explain what is going on inside a black hole, and we have not yet managed to do this. It may one day turn out that singularities do not exist in the hearts of black holes at all, but this is the extent of our knowledge so far. Well, whatever it is that lies inside a black hole, it powers our faster-than-light engine, because like most objects in the universe, it spins. And oh, does it spin! As we travel out from the center of the black hole, we pass through the event horizon with little fanfare. The event horizon actually cannot be detected locally, although a person outside the black hole might watch you slow down to a complete stop as you travel through it. From your perspective, it actually might seem like time is flowing normally. Normally, that is, until the universe outside the black hole runs its course in an instant, because time outside the black hole is traveling so fast compared to you. This is the essence of relativity. In fact, the only evidence you might have that you've passed the event horizon at all is because of something that exists just outside it, the photon sphere. In a zone just outside the event horizon, there exists a point in space where if a photon enters it at just the right angle, it will enter a perfect orbit around the black hole in much the same way the moon perfectly orbits the Earth. This infinitesimally thin zone is known as the photon sphere, and given the number of photons that have flown past black holes in all the millions of years they have existed, it is probably filled with photons. It is quite possible that you would be instantly fried as you pass through this point. However, it is just outside here that we find the zone that interests us, the ergosphere. This is the zone around a black hole where we can most easily detect its spin, and this is because, in this zone, it is impossible for us not to move. You see, mass affects space. We see this in the curving effect of gravity on the travel of objects through that region of space. However, it might be more accurate to say that mass drags on the space around it. As it moves through space, it brings a little bit of that space along with it for the ride. And when an object as massive as a black hole spins, there is an effect known as frame dragging. To put it simply, reality around the black hole begins to spin in a whirlpool that cannot be fought against. Much like a real whirlpool, anything caught within the ergosphere is spun around the black hole, because the frame of reference it sits in is being pulled. Sort of like how a person moves because they are standing on a moving walkway. The greater the spin of the massive object, the faster this happens. And in the ergosphere, this can occur at a speed so fast that by the event horizon, space is moving faster than the speed of light. You would need to travel faster than the speed of light in the opposite direction just to stay at a relative standstill from the point of view of the outside observer, which of course you cannot do. But isn't this against the laws of physics? Doesn't Einstein say that nothing can travel faster than the speed of light? The answer to that is yes, but black holes have found an interesting loophole. You see, this rule only applies locally. Right where you are, in your frame of reference, nothing can go faster than the speed of light. But thanks to relativity, it is possible for frames of reference to move away from each other so fast that objects in them appear to be breaking this light barrier from your point of view. But if you move next to them and entered their frame of reference, they would seem to slow down and would start obeying the laws of physics again. It's a really weird effect, but frame dragging is an actual thing. It is by measuring frame dragging that scientists can learn the spin of a black hole. However, according to a man called Roger Penrose, there may even be a way of exploiting it. If you were to send a rocket into this section of the ergosphere, the rocket would speed up due to being caught in the whirlpool of reality. Once it had gained enough speed, it could then fire a propellant in such a direction that it pushed itself out of the whirlpool again, but now traveling at a much faster speed. This method, named the Penrose process, could hypothetically net you energy equal to about 20% of the mass of your rocket. Now, that might not sound like much, but remember, according to Einstein's E equals mc², your 20% mass would produce energy equal to itself times by 299,792,458 squared. That's a lot of energy. So to harness this colossal kinetic energy, all you would need to do is travel to the nearest black hole, which is roughly 3,000 light years from us, and enter its ergosphere with a rocket capable of surviving the intense gravitational forces there. Ideally, you would need to find one that was not surrounded by an accretion disk, because those get up to temperatures of millions of degrees, as they are swung around at near light speeds and melt from solids down to gas and plasma. But you get the idea. Easy.
Some devote their entire lives. All we need are the moments. Full-time, part-time, in or out of uniform. How many moments can you give?
What if you were a global energy company with customers in different places on different systems? So you call in IBM and Red Hat to create an open hybrid cloud platform. Now data is available anywhere securely. Let's create a hybrid cloud that can change an industry. IBM, let's create.
Okay, maybe this is a little impractical for us, but the implications for faster than light travel that black holes demonstrate through frame dragging might just offer us the key to one day beat the light barrier for real. Not by going faster than light ourselves, but by somehow convincing the frame of reference we are in to travel at those faster speeds, just like they do around a black hole. Of course, if this requires the energy of a black hole to accomplish, we might be out of luck for now, but it's an incredible glimpse into what is possible, and scientists are already looking into the power of frame dragging for future travel. But maybe that's a topic for another video. Either way, this all just highlights once again how our universe really is very different from what we might have ever imagined. And here's another surprising thing about black holes you may not have known before. Falling into a black hole is a lot harder than it sounds. You might expect it to be relatively easy. After all, aren't these the ultimate absorbers, quite literally the largest sources of gravity out there? Shouldn't it be easier to fall into them than any other thing in the universe? You might have thought so, but paradoxically, your intuition is wrong. These galactic maws are one of the hardest places in the universe to actually get inside. So much so, during his lifetime, Einstein believed you couldn't get inside them at all. And not only that, but black holes might even eject you away from them at speeds close to the speed of light. Shouldn't it be that these objects would be incredibly easy to get into? Like a slide that gets steeper and steeper the further along it you go, you might expect to speed up more and more the closer you get to the black hole center. However, while this is right, it is also wrong. You do speed up, so much so that your speed will begin to approach the speed of light. However, in almost all circumstances, you will not find yourself approaching the center of the black hole. And this isn't me talking about some strange quirk of time or relativity, but something that will be observable from whatever frame of reference you're watching from. Confused? Don't worry, allow me to explain through the real-world example of something called an accretion disk. Black holes are, at their very heart, very simple. In something known as the no-hair theorem, black holes are said to be devoid of almost any feature, just like a head with, well, nothing on it. The features of a black hole are usually fairly plain too. They have charge, mass, and spin, and that's about it. As such, accretion disks are not actually a necessary part of black holes. Black holes can exist just fine without them, sitting there, dark and unobservable in space. However, when mass, such as an unlucky star, strays too close to the black hole's gravitational pull, it can be torn apart by the vast forces at work and sucked towards the black hole's center. Strangely enough though, this matter does not all immediately fall into the black hole's event horizon. Instead, the matter usually coalesces into a sort of flat ring that orbits around the black hole outside the event horizon. While eventually it does all enter, this process can take a long time. Some accretion disks take 100 to 1,000 million years to be completely absorbed. So what is going on here? why does the matter not simply enter the black hole? The answer is that it comes up against a surprising principle of physics known as the conservation of momentum. First described by mathematician John Wallis in 1670 and then pioneered by his contemporary Newton a decade or so later, the idea goes like this. If you have a group of objects, the motion of those objects, aka their momentum, collectively must always remain the same. If one particle with momentum bumps into a particle that is standing still and both bounce away from each other, the amount of total motion for the two particles must equal the amount of the first particle on its own. No momentum can be lost. If you have a rocket on a launch pad with zero momentum, it can only give itself momentum by firing a propellant in the opposite direction. Once you add up the amount of momentum imparted to the air by the propellant going down, and the amount of momentum given to the rocket by going up, then the upward momentum and the downward momentum are equal, resulting in the same net zero momentum you had to start with. This falls a little outside our expectations. After all, we as humans often stop and start walking around, seemingly without obeying this law. However, if you evaluate all the particles involved, this law is always kept. You would struggle to move anywhere without a floor to push against. Momentum imparted to the floor must equal the amount of momentum imparted to you, but in the opposite direction. You just don't notice it because the floor is so much bigger than you. The amount of momentum you give to it does not move it in any noticeable way. But what has this got to do with falling into a black hole? Well, consider this next example, this time to do with angular momentum. Imagine a ballerina who has their arms outstretched and is spinning on a single point. The particles in their hands have momentum. They are moving a certain distance in a certain amount of time. However, when they tuck their arms close to their body, what happens? Well, they suddenly start spinning much faster. This is a classic example of momentum trying to be conserved. You see, the momentum in the hands is still trying to travel at the same speed it was previously traveling at. However, suddenly because it's close to the body, it's traveling a much smaller distance. It is doing so at the same speed. Effectively, it has much less distance to travel to complete one revolution, and as a result, completes that revolution much faster. This causes the ballerina to spin faster when they tuck their hands in, and slower when they stretch their hands out. In most scenarios, particles will fall in a perfectly straight line towards a black hole. Almost always, this is likely and will start spiraling in towards the center, that is called the black hole's gravity. As it gets closer towards the center of the black hole, it starts speeding up, moving at nothing in the universe can travel faster than the speed of light. So what happens further and further into the black hole? Due to forces, eventually it reaches a point where it cannot go any faster. But it go further. Taking place at light speed, things get very cold. Matter in a black hole's accretion disk can reach temperatures up to 10 million Kelvin. This is enough to melt anything down to a plasma, causing them to give off more and more viscosity, like squeezing a lemon. sun such disks can reach brightnesses that exceed 1,000 times the total brightness of every star in the Milky Way combined. The good news is more gets shed by igniting it to matter further up out of the accretion disk as faster moving particles an extra push and slowing down the lower particles. In this way, matter starts to lose its angular momentum in the black hole itself. More momentum they're jets. Everything about these jets, how they form and what they are comprised of, and only a small fraction of black holes with accretion disks have them. But current theories suggest that they are caused by magnetic forces that are created by the spinning accretion disk, or even the rotational power of the black hole itself, which draws up material from the accretion disks and fires them out into space. It's likely that as the accretion disk spins, magnetic fields form, in keeping with Ampere's law, due to all those moving electrically charged particles. The power and shape of these fields are such that there is only a narrow channel at the north and south poles of the black hole for particles to escape. These magnetic fields may work in a similar way to the rifling on a gun, channeling particles down a narrow barrel. Particles moving at near relativistic speeds have only one direction they can go, even though we don't quite know yet why they go. Perhaps they are like the steam of a kettle, fired out through the only gap that exists in the face of this incredible gravitational and heat pressure. And when they go, they go. Relativistic jets travel further than the galaxies they originate from, and are often millions, if not billions, of light years long. One jet with this catchy name has its X-rays reaching Earth from 12.7 billion light years away, albeit faintly. This is because the radiation produced by such jets is very focused in one direction. In an effect known as relativistic beaming, or the lighthouse effect, when the beam is pointed away from us, it is much harder to see. Take for example the now famous M87 galaxy. Here, very clearly, a relativistic jet is detected by Hubble. This is the one coming towards us. There is very likely another jet, but we can't see it because it's going in the other direction. It's worth noting that this energy does not come from the black hole directly. Remember, nothing can escape from a black hole. Instead, the matter and radiation come from the accretion disk surrounding the black hole. And again, a lot about these jets is still theoretical. We can see them, even observe them moving over time, but we don't fully understand them or what causes them. Our understanding of accretion disks does not even fully explain how conservation of momentum is kept. There is still some mystery about where all the momentum goes, but the sheer power at play is undeniable. Einstein may have been wrong. It evidently is possible to fall into a black hole, but when some black holes are firing material away from them at near relativistic speeds for distances spanning galaxies, well, it's evidently possible to not fall into them too. And once you factor in the force of matter that is millions of degrees hot, pushing out at you as they attempt to shed their own momentum, perhaps you wouldn't want to get too close to one anyway. So, we've seen how the awe-inspiring effects of a black hole can span entire galaxies, but it begs the question, how big can a black hole actually get? Finding the largest black holes is not difficult. All you need to do is look at the center of large galaxies. These supermassive black holes have grown since their formation billions of years ago. More and more matter fall into them, continually increasing their mass. The very largest of these supermassive black holes can be billions of times the mass of our Sun. However, it may come as a surprise to you to realize that some of the most massive black holes we know of are actually the youngest. You see, when we look at distant galaxies, we are also looking back in time, and the galaxies billions of light years away often have the largest black holes. If the universe is only 13.8 billion years old, and light takes billions of years to reach us, that means the galaxy we are observing can only be a few billion years old at most from our perspective. Pretty young for a galaxy. Surely though, it should be the case that nearer and thus older supermassive black holes are more massive, seeing as they've had so much extra time to consume matter falling into them. So what's going on here? The very largest supermassive black hole we know of is known as TON 618, with an incredible mass of 66 billion solar masses. By itself, its mass is comparable to the Milky Way galaxy. However, TON 618 is exceptionally far away, and it's taking light emitted by it 10.8 billion years to reach us, meaning we are observing it as it was 10.8 billion years ago. This means it can be at most around 2.8 billion years old. By comparison, our own Milky Way galaxy is approximately 13.6 billion years old. Yet the supermassive black hole found at our galaxy's core, Sagittarius A star, is only 4 million solar masses. The Andromeda galaxy's supermassive black hole, while bigger, is still only 200 million solar masses. One of the big factors to consider here is the difficulty in detecting and measuring black holes. This is still a really new field of research, as technology has only just allowed us to start observing black holes in the last few decades. Even then, we can often only observe the area surrounding black holes, that is, before the Event Horizon Telescope came along. But even that telescope takes ages to image just one black hole, so our general understanding really is still quite limited. In fact, most of the distant black holes we know about can only be seen because they are quasars. TON 618 is a quasar. Matter is pouring into the black hole's accretion disk at an incredible rate, and because of this, it's erupted into a quasar. Quasars can only be sustained as long as matter is falling into them, otherwise they revert back to dark black holes. It's hard to fully grasp the physics of the accretion disk, but it is believed that the friction here is so great, the accretion disk of a quasar by itself can produce thousands of times more light than entire galaxies combined. TON 618 produces as much light as 140 trillion suns, completely outshining the galaxy it resides in to the point that we can't even see it from our perspective. However, because quasars are the brightest objects in the universe, they can be seen from very far away. So, one reason for large black holes being far away is down to something known as Malmquist bias. This is where brighter objects further away appear more plentiful, when in reality, you simply can't see the dimmer objects at that distance, implying there may be an argument that the largest supermassive black holes are actually distributed fairly evenly throughout the universe. If a galaxy has a very large black hole but it's not a quasar, it means we won't see it after a certain distance because a galaxy is much dimmer than a quasar. Another reason why we don't see the biggest black holes close to us is due to the nature of the universe itself shortly after the Big Bang. As you may know, the universe is ever expanding, and during the early universe, matter was a lot closer together. Quasars were more common back then because they need extreme amounts of matter falling into them to give off light, and there was a lot more gas around during the early stages of the universe. Not only has the universe expanded, but over time, gas gets converted into stars. Some of the largest types of stars eventually turn into neutron stars and black holes themselves, meaning that they never get recycled back into gas. Less available gas means less gas will fall into a supermassive black hole. One of the theories for the fate of the universe is actually based on this, called the Big Freeze, where after some trillions of years, all the gas in the universe is eventually converted into black holes. Even now, we see some galaxies where their gas has been completely used up, meaning no new stars can form. These are called elliptical galaxies. Spiral galaxies still have gas and dust structures, and thus can still produce new stars. It is interesting that most of the largest supermassive black holes appear to be in elliptical galaxies where there is no gas left. Gas needs to lose momentum to fall into the galaxy's central supermassive black hole, and if that happened, then the supermassive black hole is likely to be much bigger because of all the infalling matter. With elliptical galaxies, this has already happened, whereas with spiral galaxies, this hasn't happened to the same extent. One such trigger for gas losing angular momentum could be the gravitational influence of nearby galaxies, or even collisions with other galaxies. In addition, there is less gas available in the universe now than there was during the early universe, so black hole growth probably occurred rapidly then, but has slowed down now. This might be why there is no quasar within 500 million light years of us. As the universe ages and things become less chaotic and more spread out, the number of active quasars has decreased, which means the only quasars we see, some of which are the largest black holes we know of, are the ones that happened a long time ago. So, why are the largest supermassive black holes often the youngest? Well, though it may appear that way, it might not actually be the case at all. We can measure distant bright quasars simply because we can see them. Older and closer black holes may also be large, but because of Malmquist bias, we haven't found them yet. As studies continue and technology improves, we'll start to get a more complete picture of the universe around us.
So there we have it, almost everything you could want to know about black holes. Is there more to be discovered about them? Almost certainly. But one thing's for sure, they have completely distorted my concept of what is normal in this universe of ours. If you found value in this video, be sure to subscribe and like, and even share with someone that may enjoy it. Thanks to my patrons and members for your support. If you want to add your name to this list too, check the links in the description below. All the best, and see you next time.
Ooh. I'll be the judge of that.
Oh, that's nice.
Searchable, verified reviews.
That's better than the ham, and I've never said that.
Booking.com, booking.
Yeah.
There's a way to make an entrance.
My destiny.
It was now a conspiracy of witches.
Download Veely today.
For those who would journey across the vast reaches of interplanetary space, the solar system offers many breathtaking sights. But nothing quite compares to this. A giant world made of gas, completely encircled by a perfect gleaming set of rings. Cosmic illusion, conjured out of the infinite expanse of space, Saturn delights the eye and challenges the imagination. Yet Saturn is no illusion. It is an exotic natural laboratory that can help shed light on how planets form and perhaps on how life evolved.
4, 3, engine start. 1, 0, liftoff.
In July 2004, after traveling in space for nearly 7 years, NASA's Cassini mission arrived at Saturn. marking the start of a bold new chapter in solar system exploration. Cassini is not the first spacecraft to reach Saturn, but it is the first to remain in orbit around the planet. It is also the most expensive and ambitious planetary probe in history, gathering data and images over a long period that have completely revolutionized our understanding of Saturn and its many unique features. From its swirling, dynamic atmosphere, to its dozens of exotic and mysterious moons, to the trillions of floating bits of ice and dust that together make up Saturn's intricate system of rings. And with so much to explore, Cassini would need all the time it could get. When Cassini was launched, scientists hoped that their spacecraft would survive for 4 years. In fact, Cassini has more than doubled that. And after 8 years and counting, it's beginning to reveal details that a shorter mission would have missed. Details that will ultimately help scientists solve some of Saturn's most baffling mysteries. It's easy to understand why the extra time has been so important for Cassini. Just consider how profoundly things can change on our own planet, simply by watching the yearly cycle of the seasons. Without taking a single step, the journey from winter to summer is like a trip to a whole new world. Like Earth, Saturn is also a planet of seasons. The difference is that because Saturn is so far from the Sun and its orbit so large, a year on Saturn takes nearly 30 years on Earth. When Cassini first arrived at Saturn, the planet's southern hemisphere was in the midst of late summer. The South Pole was tilted toward the Sun, giving Cassini's cameras a superb view of the planet and its rings from below. But over the next several years, as Saturn proceeded along its orbital path, southern summer gave way to northern spring. As the seasons changed, so too did the angle of the Sun, and Cassini's cameras faithfully recorded a fascinating transformation. Month by month, the North Pole slowly emerged from darkness, while the broad shadows of Saturn's multiple rings gradually narrowed and shifted. By August of 2009, Saturn was at equinox, and for the first time in 15 years, sunlight was shining directly onto the planet's equator. At equinox, the Sun illuminates the rings from the side so that their shadows on the planet below converge into a single pencil-thin line, dividing Saturn evenly in half.
As I'm in the midst of applying for residency right now, wish me luck, Grammarly has again been a lifesaver with my application.
While across the vast ring plane, a host of rare and striking visual effects appear. Here, a narrow opening in the rings seems to be the work of a cosmic scalpel, but appearances are deceiving. What seems to be a cut in the rings is simply the shadow of Saturn's moon, Mimas, stretched out across the ring plane. Such tricks between light and dark, rings and moons, can only be observed near the time of the equinox, and they are fleeting. Here, Cassini tracks the shadow of a different moon, Tethys, sweeping over the rings in a matter of minutes. Looking more closely, the same effect allows Cassini to spot something new, a tiny moonlet just 300 meters across, embedded within the rings. Such objects are normally invisible, but during Saturn's equinox, their presence is revealed by the shadows they cast. Here, a jagged line of shadows reveals not just a single moon, but what appears to be an entire mountain range towering 2.5 kilometers above the ring plane. These peaks may be more like clouds than mountains. Puffs of dust-sized particles deflected upward by larger chunks of icy material orbiting within the thickest and brightest portion of Saturn's ring. Meanwhile, as the sun begins to warm the planet's northern hemisphere, there is more for Cassini to discover. Not just in the rings, but in the hazy depths of Saturn's atmosphere, where a dramatic change in the weather is about to unfold. For the planet Saturn, 1.5 billion kilometers from the sun, the concept of summer is a relative term. Here, at the outer reaches of the solar system, the sun is just 1% as bright as we experience it on Earth. That's far too weak a light for solar panels to be of any use. So the Cassini mission to Saturn relies on the decay of nuclear isotopes to power its planet and electrical system. Yet as the seasons change on Saturn, there are signs that the sun can still have a profound effect on this majestic planet. By late 2009, Cassini had been in orbit around Saturn for over 6 years. It had witnessed Saturn's spring equinox and was watching closely as summer approached for the planet's northern hemisphere. The change brought more light and more heat to the northern half of Saturn's hazy, cream-colored atmosphere. Saturn's clouds are over 100 kilometers thick. Their tops are made of frozen ammonia ice, but far below there is a layer of water vapor. And as heat generates turbulence in these clouds, the result is lightning. In November of 2009, Cassini's cameras, for the first time, witnessed an electrical storm rattling the night side of Saturn. And just like on Earth, the bright flashes of electrical energy came with bursts of radio static. Clearly, the changing seasons had awakened something in Saturn's atmosphere. 1 year later, on December 5th, 2010, Cassini snapped this image of Saturn on the same day the spacecraft's radio and plasma experiments detected lightning in the atmosphere. Although no one realized it at the time, this image contains the first hint of a giant storm about to erupt in Saturn's atmosphere. In this first image, the storm appears as a tiny spot relative to the planet, even though it is already 2,000 kilometers across and growing fast. Within 3 weeks, the spot had evolved into a vast and complex storm system with towering clouds of white ammonia crystals. For months, the great storm raged on, becoming one of the largest disturbances ever seen on Saturn. Over the course of 2011, Cassini's electronic eyes revealed the storm's progress in unprecedented detail, using its infrared vision to peer further into the planet's unsettled atmosphere. False color views like these helped reveal the storm's structure. Here, red indicates the deepest levels exposed by the storm's churnings. Eventually, the storm wrapped itself all the way around the planet, forming a continuous band of chaotic turbulence. For an entire year, it had given scientists their best chance ever to witness the complex workings of Saturn's atmosphere in action.
Remember this, and the false selector scheme.
Scientists still have a lot to learn about how Saturn changes with the seasons. And those changes don't just apply to Saturn's atmosphere, but to its largest moon, Titan, one of the most intriguing destinations in the solar system. Titan is more than a moon. It is like a planet unto itself, with a dense atmosphere made of nitrogen gas and a thick orange-colored haze layer that acts like a natural smog. Although the smog conceals Titan's surface from view, it only serves to raise scientific excitement about what kind of world may lie underneath. Even before spacecraft were sent to Saturn, astronomers realized that conditions on Titan's surface were bound to be interesting, because temperatures and pressures there allow methane to exist as a liquid, a solid, and a gas. Could Titan have rivers and lakes of liquid methane? That is the question scientists hope to finally answer with Cassini. In October 2004, 3 months after arriving at Saturn, Cassini was scheduled to make his first close pass of Titan, and expectations were running high. The results were astonishing. Through its infrared eye, Cassini could see that the surface of Titan was far more interesting than anyone had expected, with a sharp separation between light and dark regions that strongly resembled coastlines on Earth. Meanwhile, Cassini's radar unveiled a surprisingly diverse surface that suggested a complex geologic history. But where were the lakes and rivers of methane? Cassini couldn't tell. Because there are no shadows under the foggy haze of Titan, there's no way for the infrared camera to reveal whether the light or dark areas were of different elevations. However, in close-ups, all of the areas seem to be windswept, suggesting that both the light and dark areas seen here are just different kinds of dry land. Fortunately, Cassini had one more tool to help make sense of what it was seeing on Titan. The Huygens probe, built by the European Space Agency, had come to Saturn attached to Cassini. In January of 2005, Huygens released itself from the main spacecraft and plunged into Titan's enveloping haze. There, its cameras radioed back an important discovery, an aerial view showing some dark, branching channels that had clearly once been carved out of Titan's surface by some kind of flowing liquid. Amazingly, Huygens even continued operating after it hit the surface. Its final image was a tantalizing view of an alien terrain, littered with what looked like rocks, rounded by the action of a flowing liquid. Scientists knew the rocks had to be chunks of water ice, which at the extremely cold temperatures on Titan's surface behave like solid rock. But where was the liquid that had flowed over them and carved the channels? To understand what they had found, Cassini's scientists would need a change of season. When NASA's Cassini spacecraft journeyed to Saturn, the planet's giant moon, Titan, had the largest unexplored surface in the solar system. And when Cassini's infrared camera finally peered through Titan's impenetrable clouds, scientists found a world strangely divided into territories of light and dark. The light areas were easy to explain. Like Saturn's other moons, Titan's surface is mostly made of ice. But the dark regions that ran along the giant moon's equator were a puzzle. Was this the liquid methane that scientists had expected to find flowing over Titan's frozen surface? The answer proved to be more complicated. Although these dark plains may have been flooded by liquid in the past, what Cassini found looked more like dry land. Using its radar system to bounce signals off of Titan's surface, Cassini revealed row upon row of wind-blown dunes. The dunes reveal that Titan's dark equatorial zone is more of a desert than a sea. So to look for signs of liquid on the moon's icy surface, Cassini turned its attention to Titan's poles. It was here that Cassini saw its first obvious signs of weather on Titan, in the form of thick white clouds of methane circling around the South Pole. In time, Cassini would see many more methane clouds on Titan. As the season changed and sunlight shifted northward, they began appearing over Titan's equator and the North Pole.
Hey, Seth, getting ready to roll?
Yep, rolling with Verizon, and I got this incredible iPhone 14 Pro on them.
So you got an amazing network and save money doing it.
That's right. Get iPhone 14 Pro, Apple Watch SE, and iPad. All three on us. On the network you want. Verizon.
Google Fi, a phone plan by Google. Get up to $899 back on the Samsung Galaxy S23 Ultra with qualifying trade-in.
The clouds proved that Titan was a dynamic world with a restless atmosphere. But did Titan's shifting patterns of clouds also mean rain? On Earth, rain is the way that evaporated water returns to the surface, forming rivers and lakes. On Titan, conditions should be just right for methane to behave in the same way. The first clue that this is happening was this large dark spot found near Titan's south pole. Unlike the dark regions near the equator, this one had no dunes, but sharp boundaries and a shape and size that reminded scientists of one of Earth's Great Lakes. They called it Ontario Lacus. The more Cassini peered at Ontario Lacus, the more this strange dark feature seemed like a liquid body. By taking advantage of the spacecraft's radar views from different angles, scientists were even able to construct a computer-animated flyover. There are beaches here, formed by the action of moving waves. There are inlets and bays where liquid has flooded in. And there are even river deltas where dark channels appear to flow into the lake. There seems little doubt that Cassini had at last found a body of liquid methane on Titan. Now Cassini turned its attention northward, beyond the dark dune fields near the equator, and up into regions still emerging from Titan's cold, dark northern winter. What Cassini discovered there looked very much like a landscape inundated with lakes. In radar images, they stand out like pools of black ink against a ghostly white icescape. And then something much larger. Hints of a vast and jagged coastline with jutting peninsulas and great islands. It was to be Cassini's first close-up glimpse of Titan's largest liquid feature. This is Mare Kraken, the Kraken Sea, named after a legendary sea monster. As large as the Caspian Sea on Earth, Mare Kraken spreads across so much of Titan's northern landscape that its full extent has yet to be mapped. The more data Cassini gathered, the more obvious it became that it's the northern half of Titan where fluid is most concentrated. And in case anyone needed more convincing, on December 17th, 2009, Cassini spotted something that scientists had long been hoping to see. It is the glint of sunlight reflecting off the mirror-like surface of the Kraken Sea. This telltale flash is the final piece of evidence that Titan truly is a world of lakes, the only world in our solar system, apart from Earth, where liquids exist naturally on the surface.
In one sense, Titan presents us with an utterly alien landscape where water behaves like solid rock and methane gas behaves like water. But because there's an atmosphere on Titan, with wind and rain, lakes and rivers, something about this alien landscape also reminds us of home. It's not Earth as we know it, but it shows us where our own planet fits into the larger family of possible worlds, all shaped by the same phenomena. Scientists are now considering future missions to Titan that could include dropping a boat onto one of its lakes, or perhaps the Kraken Sea. Such a spacecraft would become the first mariner to sail beyond the seas of our own planet and reveal the unknown wonders that lie await on these distant shores. When that day comes, it will not only teach us more about Titan, but confirm what the Cassini mission has shown us over and over again. That while seasons may change on Saturn, our capacity to be enchanted by this remarkable planet and its moons endures without end. But in the process of doing so, it may also reach back across billions of years of cosmic history. On Earth, tracing that history presents an enormous challenge. The ceaseless movements of water, ice, wind, and
Starting an online store is easier than you think. Let me show you how to quickly open one with Shopify.
volcanic eruptions, as well as the actions of a diverse and complex array of living organisms, all combine to create a planet that is never at rest. Our world is a world of the present, a world of change. To access our past, we must leave Earth behind and find those places that time has left untouched. On September 17, 2007, a NASA spacecraft began the most ambitious journey yet back through the 4.5 billion years of our solar system's history. Its goal? To open a window into a distant era when the planets as we know them today were still just forming. Fittingly, it's called the Dawn Era. While the secrets of the solar system's early history remain elusive, the place to hunt for those secrets is not. It is the asteroid belt, a zone of flying rocks and miniature worlds that forms a vast ring of material orbiting around the sun. The asteroid belt is a place of transition between the inner solar system, where small rocky planets like Earth are found, and the outer system, where the planets are massive spheres of liquid gas. And it's here that scientists are seeking insights into a different transition. The one that billions of years ago led from small bits of cosmic dust and debris to the planets that populate our solar system today, including at least one such planet, our own, that is capable of supporting life. There are hundreds of thousands of objects in the asteroid belt. Most are only a few kilometers in size, tiny flying mountains that tumble namelessly through space. But a handful of asteroids are hundreds of times larger than that and much more interesting. In fact, they are just large enough to reveal the first steps on the way to making true planets.
Dawn's mission is to explore the two most massive asteroids, Ceres and Vesta. Both were discovered more than 2 centuries ago, even before astronomers realized there was such a thing as an asteroid belt. Now they are believed to be relics from a far more distant past, when objects that were several hundred kilometers in size became the building blocks of the solar system's rocky inner planets. Where such objects can still be found. But even here, they are rare. Most of them were broken apart by collisions with other asteroids long ago. As the largest survivors of the celestial shooting gallery, Ceres and Vesta are especially important to scientists. But until now, the best views we've had show them as little more than blurry, uneven blobs. The Hubble Space Telescope has taken enough images of Vesta to show the asteroid rotating on its axis. But there is only so much that can be learned from this distance. So, with a sophisticated huge instrument and a long list of questions, the Dawn mission set out for the asteroid belt, with Vesta as its first stop. Earth's gravity, Dawn spread its 2 enormous solar panels, giving the spacecraft the appearance of a great bird in flight. The panels are part of an innovative propulsion system that generates electricity from sunlight and uses it to drive a high-speed stream of ionized xenon. This method has proved ideal for pushing Dawn along its complicated flight path, which took it past Mars in 2009 and onward into the main asteroid belt. But this is not the first time spacecraft have explored this rocky region of the solar system. In 1991, the Galileo mission on its way to Jupiter passed near enough to the small asteroid Gaspra to return this image, the first ever asteroid close-up. 2 years later, Galileo passed a much larger asteroid named Ida and discovered that it was circled by a tiny moonlet, which scientists dubbed Dactyl. In 1997, the Near-Shoemaker spacecraft saw a very different-looking kind of object when it passed near the asteroid Matilda. And finally, in 2010, Europe's Rosetta mission captured this view of Lutetia. At over 100 kilometers across, it was the largest asteroid yet to be revealed. Yet all of these views, taken by spacecraft.
With the Wells Fargo Active Cash Card, you earn 2% cash back on what you want, like first date plans and need.
No. Just my shoe.
Like maybe shoes without laces. The Wells Fargo Active Cash Card. That's real life ready.
Did you know you could save hundreds a year on groceries at Aldi?
It's true!
It's not a sale. It's an Aldi thing.
On their way to other destinations are tantalizingly brief. This time, scientists were planning for a very different kind of encounter, one that would allow them for the first time to orbit and survey in detail the 2 giants of the asteroid belt. By July of 2011, that encounter was set to begin. After 4 long years, Dawn was finally approaching its first stop, Vesta. As Dawn's cameras zoomed in on their target, scientists prepared to open a new chapter in asteroid exploration. They would not be disappointed. 350 million kilometers from the Sun, the battered surface of the asteroid Vesta bears witness to the solar system's violent beginning.
mission, the first spacecraft to closely examine Vesta in an effort to tease out some billion-year-old secrets about the formation of the planet. Although it is one of the largest asteroids of all, Vesta is tiny compared to Earth, with a surface gravity that is only 2% what we experience on our world. Yet even such a tiny gravitational pull is enough to keep Dawn in orbit around Vesta. And soon after it arrived, in July of 2011, the spacecraft set about imaging the asteroid's entire surface end to end. Like other asteroids, Dawn has found that Vesta is riddled with craters. Each crater marks the spot where another smaller object has pounded Vesta's surface at high speed. Some craters are more recent than others, with clear, sharp edges. This group of 3 craters, imaged shortly after Dawn arrived at Vesta, is nicknamed the Snowman. Other features are more mysterious. As Dawn first approached Vesta, one of its first discoveries was a set of deep parallel troughs running roughly along the asteroid's equator. Although these troughs are not craters, Dawn scientists would eventually realize that they too are related to the large-scale collisions that have rocked Vesta in the distant past.
The fate of an asteroid is determined by its encounters with others. In the early days of the solar system, asteroids such as Vesta were built up from smaller bodies that collided and stuck together.
Many of these early clumps continue to grow and combine, forming full-sized planets like Earth. But in the location that is today known as the asteroid belt, it's thought that the strong gravitational influence of Jupiter, the solar system's largest planet, scattered the asteroids and kept them from forming something larger. Instead, many were broken apart by collisions, with fragments still occasionally raining down on Vesta right up to the present time. What makes Vesta an exception is that it has survived at its current size. Relative to most other asteroids, Vesta is a giant. And while it may look like an asteroid on the outside, there is evidence that Vesta could have a planet-sized heart. Most asteroids are thought to be the same inside and out. They have been built up bit by bit out of the dust and debris that swirled around the sun when the solar system formed over 4.5 billion years ago. Dark and primitive, they are rich in carbon, oxygen, and other elements that are common throughout the Milky Way, the byproducts of the life cycles of the star. Vesta is known to be very different. By analyzing the sunlight that reflects off its ash-gray surface, scientists have found it is more like basaltic rocks found on Earth. Such rocks are created in the heat of volcanic activity, created when lava cools on or near Earth's surface. There are also meteorites with a similar composition, space rocks, thought to be pieces of Vesta, which were blasted off the asteroid and later tumbled to Earth. These precious fragments suggest that Vesta was a molten body in the distant past. But how could such a small, cold world have produced lava? The answer lies with the star. Supernova.
Hey, Seth, get ready to roll?
Yep, I'm rolling with Verizon, and I got this incredible iPhone 14 Pro on them.
So you got an amazing network and save money doing it.
That's right. Get iPhone 14 Pro, Apple Watch SE, and iPad. All 3 on us. On the network you want, Verizon.
What is he doing here?
Is the sudden death of a massive star and one of the most violent events in the universe. For a brief moment, a supernova can outshine all the billions of stars in the galaxy combined. As the explosion rips the star to shreds, matter that has been highly energized by the supernova flies off in all directions. Of the many kinds of atoms that are created in a supernova, one of the most important to astronomers is aluminum-26, a radioactive isotope that decays over hundreds of thousands of years. Because aluminum-26 is known to have been present as our solar system was forming, scientists now believe high concentration of this material is what gave Vesta its original heat billions of years ago. But today, as dawn patrols Vesta's pockmarked surface, there seems to be no obvious traces of past volcanic activity. In a search for settler clues, dawn has paid close attention to the deepest part of Vesta's surface, near the asteroid's south pole. Even before dawn arrived, scientists knew there was a dark feature here, which they quickly realized was the shadowed hollow of a giant impact crater. Scientists have named the crater Rhea Silvia. This computer-generated perspective, based on dawn imagery, shows what it would be like to swoop down on Rhea Silvia and fly around its outer perimeter. By adding false color, where red represents high elevation and blue the lowest areas, it's possible to see the structure of this enormous crater more clearly. Rhea Silvia is, without a doubt, the largest and most impressive feature on Vesta. Nearly 500 kilometers across and 19 kilometers deep, it has a central mound that is more than double the height of Mount Everest. And as dawn moved in for a closer look, it was soon clear that the giant crater was just as impressive in its details. Here, jagged cliffs protrude from the wall of Rhea Silvia, revealing the bedrock that lies beneath a thick blanket of impact debris. Further down, smaller impact craters with scattered boulders gouged out of Rhea Silvia's low-lying floor offer the most revealing glimpse at a part of Vesta that was once deep below the surface. Armed with these and other unprecedented views, scientists would soon discover that Rhea Silvia was the key that would help them unlock the 4.5 billion-year-old history of Vesta. But along the way, that key would also provide an unexpected challenge. By April of 2012, NASA's Dawn spacecraft had brought itself to within 200 kilometers of the asteroid Vesta, much closer than the International Space Station orbits Earth. At such close quarters, Vesta's airless surface is kept at a small crater. Many of them produce intense rocks that were beyond With dawn's help, astronomers have now confirmed that the biggest blast of all came roughly 1 billion years ago, when a smaller asteroid collided with Vesta and formed its giant crater, Rhea Silvia. Now it appears that many of Vesta's unique features are tied to this ancient impact. But when Dawn began looking at Vesta's giant crater up close, it encountered another surprise. Rhea Silvia sits on top of another crater whose outline can still be seen. Nearly as large, but 1 billion years older, scientists have dubbed Vesta's second giant crater Venenia. So now it's clear that Vesta was twice hammered by a mighty blow. Each one raised its own set of ridges and troughs, and each one excavated tons of debris that were then scattered across much of Vesta's ancient surface. But while some of Vesta's past now lies buried by these giant impacts, there are pieces of it that can be examined up close. That's because the same two impacts that carved out Vesta's largest crater also shattered its crust and mantle, blasting enough rock into space to create an entire family of smaller asteroids. It is these pieces, known as Vesta, which have occasionally found their way to Earth as meteorites, bringing us valuable clues about the nature and history of Vesta. Now those clues can be directly compared with the data that Dawn has gathered by orbiting Vesta up close. The results make clear.
Switch to Verizon and get iPhone 14 Pro, Apple Watch SE, and iPad, all 3 on us. Verizon.
That Vesta is a unique fossil from the solar system's deep past. At that time, its liquid interior divided into a metallic core and a rocky mantle, with minerals that become more iron-rich the deeper you go. In this way, scientists have found that Vesta is less of an asteroid and more of a miniature planet. An early result of the same process that would eventually lead to the formation of Earth in all its geologic diversity.
Dawn's one-year encounter with Vesta has given us a close-up view and a new understanding of the solar system's ultimate survivor. But our explorations of the asteroids and the asteroid belt are just beginning.
In the summer of 2020, Dawn's ion engine powered up and gently pushed the spacecraft out of its orbit around Vesta, putting it on course to rendezvous with the asteroid Ceres in 2015. And while Dawn moves on, scientists are also imagining even more ambitious explorations of asteroids that are closer to home. They are eyeing the so-called near-Earth asteroids, which have drifted far from the main asteroid belt and over millions of years have wandered into our own part of the solar system. The nearest of these wandering neighbors is the asteroid Eros, an irregular chunk of flying rock nearly 35 kilometers long. This was the target of the Near-Shoemaker mission, which orbited Eros in 2000 and even managed to touch down on the asteroid's boulder-strewn surface a year later. By 2019, NASA's OSIRIS-REx mission hopes to follow a similar strategy, closing in on near-Earth asteroids and capturing up to 2 ounces of material for return to Earth. Such missions hold great value for researchers trying to piece together the detailed composition and history of these nearest asteroids, and there are good reasons for doing so. Evidence suggests that in the past, asteroids colliding with Earth played a fateful role in shaping the history of life on our planet. In the future, near-Earth asteroids may become important in a different way, as a tantalizing opportunity for those seeking to harness these objects for their mineral wealth. Such a future will mean that the asteroids, which were long overlooked in the early years of space exploration, could one day become our main reason for venturing into space. And the next frontier in humanity's epic quest to reach for the stars. other planets besides our own have towering mountains and vast deserts. Only on Earth do we find this: entire oceans of water in liquid form covering much of the planet's surface. Water shapes our planet. It dissolves rock, moves energy around the globe, and helps make our climate livable. But most important of all, water lets chemicals mingle, including those chemicals that are crucial for sustaining life. Quite simply, without water, life as we know it would not exist.
Water is so important to life on Earth that finding it has become a key goal for scientists looking for life elsewhere in the solar system and beyond. In fact, we have become cosmic dowsers, feeling around for hints that even now, water is flowing somewhere out there.
The quest for water has led us to the places that at first glance seem to resemble Earth the most. Torrid Venus and desolate Mars. But surprisingly, the strongest evidence we have that water is present in liquid form elsewhere in our solar system comes from a world that is utterly different from our own.
One movie has audiences going crazy. I got a good feeling about it. Dungeons & Dragons is the best movie of the year.
That's a lot of pressure.
It's what we do. It's wildly entertaining, and it charms its way into your heart. Wonderful. Dungeons & Dragons: Honor Among Thieves.
Make room for life's biggest achievements. CubeSmart has convenient self-storage.
This is Enceladus, a tiny frozen moon of Saturn located 1.5 billion kilometers from the Sun. Although it is just one of dozens of moons orbiting Saturn, scientists have long suspected that there is something special about Enceladus. For starters, it has the brightest surface in the entire solar system. And another curious detail, Enceladus travels around Saturn embedded within a faint and diffuse band of particles known as Saturn's E-ring. Astronomers have long suspected that the E-ring is related somehow to Enceladus. But how? The question would be answered in 2005, when NASA's Cassini spacecraft began the first of several close passes of Enceladus during its ongoing exploration of the Saturn system. In some areas, the surface is clearly ancient, marked by craters that have accumulated over billions of years. But toward the south pole of Enceladus, the surface features tell a very different story. Here, the landscape is dominated by a strange pattern of linear grooves. In July 2005, Cassini was swooping in for a closer look at this area when it spotted a dramatic series of 4 deep fissures. Scientists nicknamed the strange markings the tiger stripes. During the same flyby, one of Cassini's instruments detected signs of a gaseous material above the moon's south pole. The gas was mainly water vapor. These clues made it clear that something truly unique is happening on Enceladus. So when Cassini next encountered the moon in November of 2005, mission controllers commanded the robotic probe to swivel around and capture an image of Enceladus backlit by the sun. The result was this incredible image showing jets of water vapor spewing from the south polar region of Enceladus.
These jets must be the sources of the E-ring that surrounds Saturn, and they are among the most exciting revelations of the entire Cassini mission. Captured in the sun's glare, the jets look like geysers of icy mist. Enceladus, once expected to be a cold and dead moon, seems to have a warm and geologically active interior, and the results can be seen literally spilling through the cracks. But where is the heat coming from? Enceladus is too far from the sun to be warmed by its rays. Yet it is also too small to be able to hold on to the internal heat it acquired when it formed billions of years ago. Instead, scientists suspect that somehow Enceladus is gaining additional heat from the gravitational pull of Saturn. But whatever is heating the moon, evidence is mounting that it's been going on for a long time. For example, Cassini has revealed that a blanket of snow made up of icy particles from the geysers is building up on the moon's surface. In some areas, the blanket is 100 meters thick, an amount that scientists estimate would take 10 million years to accumulate. If Enceladus has been active for that long, it may be because beneath its icy surface lies an entire ocean of liquid water. If this is true, then the geysers of Enceladus represent the most direct evidence for liquid water beyond Earth. And where there's water, there could be life. But water is a dynamic substance that brings change wherever it turns up. That's why looking for change may ultimately be the best way to find water beyond Earth. In our solar system, no other planet has intrigued, excited, and misled astronomers more than Mars. Mars is the only planet with a solid surface that can be observed easily from Earth. And for generations, its rust-colored glow has beckoned would-be explorers. First with telescopes, and then with wave after wave of robot probes. What they have discovered is a world of dry...
Take a tour of a place from the comfort of your phone.
Bono and the Ed.
Dry rivers and ancient lake beds. A world where water flowed freely billions of years ago, forming mineral deposits and bubbling through the soil in hot springs. And it is also a world where water still exists in frozen form, locked as permafrost in the Martian soil. But in all this exploring, is it possible we've missed the most important discovery of all?
Mars is a remarkable world with a complex history in which water once played an important role. Today, spacecraft are orbiting around Mars and roving over its surface in an effort to piece that history together. But in the process, they are also turning up some unexpected clues that suggest there may be liquid water lurking on Mars today, and we can find it if we know where to look.
Mars has received so much attention over the years, it may seem strange that only now are scientists beginning to spot these clues. But that is because for many decades, the exploration of Mars was a fleeting affair, with visiting spacecraft only surviving for a limited period of time. That changed starting in September of 1997, when Mars Global Surveyor arrived. It was the first of a new generation of orbiters that have had Mars under continuous surveillance ever since. And that is precisely what is needed to look for small-scale changes that could be a sign of water flowing near the Martian surface. At face value, such an idea seems misguided. After all, Mars is a freeze-dried world with an atmospheric pressure so low it's nearly a vacuum. Under such conditions, any liquid water on the surface would rapidly vaporize. But in June of 2000, scientists operating the camera on board Mars Global Surveyor reported an exciting find. In some of the tens of thousands of images, they found small gullies carved into the sides of canyons and crater walls. The gullies looked suspiciously like they were formed by water that seeped from the rock and flowed downhill before evaporating. And unlike those features formed where water flowed on Mars billions of years ago, the gullies looked recent, as if they were just formed. When they were first discovered, some scientists speculated that the gullies might be a sign that there are hidden reservoirs of underground water on Mars that occasionally spill onto the surface. It's a tantalizing possibility, one that became even more exciting when some of the gullies appeared to be changing from one year to the next. Perhaps water was responsible. But there was a catch. The gullies were typically found far from the equator, in craters or canyon walls that faced away from the sun. These cold and shaded places should be the least likely to yield liquid water. And that suggested another way to explain the gullies. Mars is so cold that during the winter months, the carbon dioxide in its thin atmosphere can settle onto the surface as frost. Such a buildup of CO2 could trigger landslides simply by adding weight or by pushing up on rock and dust when it evaporates. But there remain cases that are difficult to explain. In 2011, scientists working with the Mars Reconnaissance Orbiter, a spacecraft with the most powerful camera sent to Mars yet, reported that the orbiter had spotted a curious phenomenon in Newton Crater in the southern hemisphere of Mars. Images taken several months apart showed dark streaks rolling down the crater walls and fanning out along the flatter ground below. More streaks appear as the southern spring turns to summer. Then they disappear again at winter's approach. It's tempting to think that water is the cause, darkening the soil as it runs downhill, like a wave creeping across dry sand. But the discolorations last for months, too long for liquid water to linger near the surface of Mars. Instead, water from melting ground ice may cause a chemical or physical change in the soil as it flows just below the surface. If scientists were to verify that liquid water can sometimes occur on Mars, even briefly, the implications are enormous, because that water...
This is the most powerful demon I've encountered. But this is not about the boy. The Vatican buried the truth here.
Exclusively in movie theaters, rated R.
Monster spill? Bounty, the quicker picker-upper.
might be all that's needed to sustain hidden colonies of Martian microbes. It's an incredible idea, one that could put an alien form of life within our grasp. But even as we imagine building more sophisticated machines that will further the quest for water on Mars, another kind of spacecraft has transformed the search for water in the universe by taking it to the stars. If there is one idea about the universe that is fundamental to all others, it's that no one place in the cosmos is truly unique. In every direction in space, there are atoms, stars, and galaxies. Just as there are here, and they obey the same laws of nature. This is an extremely profound thought, because it means that if life is possible here, we should also expect to find life elsewhere, wherever conditions are right. Conditions that include liquid water. Fortunately, space travel has given us a new set of tools for exploring beyond the solar system. They are orbiting telescopes that are making it possible to find planets around other stars. And they can even tell us if some of those planets show signs of having water. One such planet, designated HD 209458b, has been found circling a star similar to our Sun. Located 150 light-years away in the constellation Pegasus, it is the first planet outside our solar system to be observed crossing directly in front of the star that it orbits. Even though the planet is too faint to be seen directly, each time it does this, astronomers can measure how much the star's light dims and for how long. This has allowed them to calculate the planet's size and its distance from the star. But it can also reveal much more. As some of the star's light passes through the planet's atmosphere, it can be used to read the chemical signatures of the gases that are present there. Space telescopes have detected the signs of an extensive atmosphere around the planet, and they paint a portrait of a world that is unlike any in our own solar system. Heated by the relentless glare of a stellar inferno, the atmosphere of the planet has expanded, forming a long tail of gas escaping into space. Closer in, the atmosphere is subject to 1,000-degree temperatures and violent winds. At such extreme conditions, and lacking a solid surface, this planet is not expected to harbor life. But in analyzing its atmosphere, astronomers in 2007 made an important discovery. For the first time, they reported evidence for water vapor on a planet orbiting another star. This is exciting, if not a complete surprise. After all, water is one of the most common molecules in the universe. But seeing its signature in the atmosphere of so alien a world means that, in principle, water may also be detected on other planets that are far more similar to our own. The job of finding those planets falls to a highly specialized space telescope. This is Kepler. It is the first telescope with a reasonable chance of detecting another Earth. Kepler does this by staring continuously at a single patch of our Milky Way galaxy. By doing so, it can monitor over 100,000 stars at the same time. Every so often, one of those stars will dim for a few hours and then return to normal. If the dimming repeats at regular intervals, then astronomers know that Kepler has found a planet. One of Kepler's most exciting discoveries to date is a planet around a sun-like star simply called Kepler 22b. Kepler 22b orbits at about the same distance Earth orbits the Sun. Just the right distance for liquid water to exist, and possibly life. But Kepler 22b is also not like Earth. Instead, it is nearly 2.5 times the size of our planet. Astronomers call such a world a super-Earth. Kepler 22b could be made entirely of rock, or it could be a planet-wide ocean, a water world. Another example is Gliese 1214b, a world that circles a small red star only 40 light-years from our solar system. This planet is similar in size to Kepler 22b, but much closer to its star. This makes it easier to measure the planet's mass because of the gravitational pull it exerts on the star as it orbits. From observations of the star, astronomers can tell that the planet is not nearly massive enough to be made entirely of rock. Therefore, it is either a small, rocky world with a vast atmosphere, or a true water world. If this is confirmed, then the notion of a planet made almost entirely of water is one of our nearest neighbors. When we search for water in our solar system and beyond, what we have found is the universe's remarkable capacity to surprise us. Instead of places that resemble Earth, we discovered Martian gullies, geyser-spraying moons, and possibly ocean planets. What all of these findings point to is the incredible variety of environments in which liquid water can exist across the continent. We find life. If our world is any indication of conditions elsewhere, then ours is a universe teeming with life. Among these, gravity plays a unique role. Only gravity to explore the universe and is showing us what telescopes cannot. Our
our gravitational exploration of the cosmos.
The next level of nerds. Nerds Gummy Clusters. A crunchy outside with a sweet gummy center. Nerds, shake things up.
Today I'm doing a supernatural sculpted look. I'll start by warming up my face. It's a yes for this NARS Laguna Cream Bronzer. This new contour and bronzer duo from Patrick Ta defines my face just how I like. Let's add a pop of color now. The Dior Backstage Blush is the obvious choice. Okay, last step. My Charlotte Tilbury highlighter wand gives such a great glow.
Cosmos begins close to home. Made up of nearly 6 billion trillion tons of rock and metal, our own planet Earth has by far the largest mass and the strongest gravity that humans have ever experienced. In fact, Earth's gravity is strong enough to hold almost anything to its surface, including soil, water, and the very air we breathe. Even the moon, a sister world hundreds of thousands of kilometers away, is held in orbit by Earth's powerful gravitational pull. But Earth's gravity is not uniform. At different points and at different times, it can be slightly stronger or slightly weaker. For scientists, these tiny differences can reveal important information about the layers of rock that lie below Earth's surface, or about the movement of water and ice at the poles and around the globe, all of which have mass and contribute to Earth's overall gravitational pull. And the best way to measure these differences is not from Earth, but from space. This is the Gravity Recovery and Climate Experiment, or GRACE for short. Launched in March of 2002, it's a joint effort by NASA and the German Space Agency to map the subtle variations in Earth's gravitational field, 1,000 times more accurately than ever before. GRACE is made up of 2 satellites, which orbit Earth in tandem and communicate with each other using a microwave ranging system. Flying about 220 kilometers apart, they make an exquisitely sensitive gravity needle. Whenever the leading spacecraft passes over a part of Earth where the gravity is a bit stronger, it feels a slight pull, causing it to accelerate and increasing the separation between the 2 spacecraft. Whenever the gravity is a bit weaker, the reverse happens, and the 2 orbiting spacecraft move slightly closer together. By repeatedly measuring these slight changes, GRACE has built up a detailed profile of Earth's gravity and revealed subtle variations across the planet's surface. Here, red represents areas where the gravity is slightly stronger. These correspond to mountain ranges and other large accumulations of mass. Blue shows where there is less mass, and the surface gravity is slightly weaker. Looking elsewhere, GRACE can also record changes that show more directly humanity's growing impact on the planet. In this view of India, red represents a decrease in gravity where groundwater has been drastically depleted by human consumption over the past decade. The quest to measure Earth's gravity with ever greater precision has become a key way to study our planet's hidden structure and monitor its ongoing transformation.
But as fruitful as this technology has been, scientists have also come to realize that there are many more places besides Earth where gravity can be an aid to exploration. Now, similar missions are envisioned for other worlds, where we have far less information about what goes on below the surface. The first of these is already underway, and as expected, gravity is providing an exciting new way of seeing what was once hidden. For centuries, astronomers have wondered about the invisible mechanism that seems to keep the moon circling around us with clock-like regularity. It was Isaac Newton who solved the riddle. He was the first to recognize that the same force that causes an apple to fall from a tree is the one that keeps the moon in orbit around the Earth. He not only discovered the law of gravity, he understood it was universal.
5, 4, 3, 2, 1, 0.
More than 200 years later, Newton's mathematical description of gravity is still used to calculate the flight path of spacecraft that leave the Earth far behind, including those that set out for the moon. In September of 2011, NASA launched not one, but 2 identical spacecraft, both heading for a lunar rendezvous. This is the Grail mission. Its objective, to use gravity to unlock some of the moon's deepest secrets. Like the Grace mission around Earth, Grail is designed to monitor changes in the separation between 2 spacecraft as they are pulled in different ways by the gravity of the body they orbit. But compared to Earth, the moon is an even better subject for this double-barreled style of mission. The most important difference is that unlike Earth, the moon has no atmosphere. This means the 2 Grail satellites can orbit much closer to the moon's surface and, in doing so, make a much more accurate gravity map. At the beginning of 2012, when the 2 orbiters arrived, they were in highly elliptical orbits that took them more than 8,000 kilometers from the moon's surface, too far for useful measurements. But over the next 8 weeks, those orbits were carefully adjusted into tight circles with an average altitude of just 55 kilometers above the surface. At that point, the 2 spacecraft were tearing around the moon at 5,000 kilometers per hour, completing 1 orbit in just under 2 hours. And like a high-definition movie in Fast Forward, the stark lunar landscape rushed by beneath them. Scientists nicknamed the twin Grail satellites Ebb and Flow because of the shifting nature of the measurements they were designed to make. With Flow in the lead and Ebb about 100 kilometers behind, they circled the moon in formation so that if one felt a slightly stronger gravitational pull from one part of the moon, the distance between the 2 orbiters would change slightly. The probe kept track of their relative positions by sending pulses of microwave energy back and forth while maintaining radio contact with Earth. Accurate clocks on board each spacecraft carefully track the timing of the microwave pulses, allowing the system to detect a change in the twin orbital separation as small as 1/10 of a micron, or roughly half the thickness of a human hair. With this remarkable precision, Grail set out to explore the moon's gravity with 100 times the resolution of any previous mission. 1,000 times for the moon's less explored far side. In this view, the best ever of the far side, the side that always faces away from Earth, we see a rough and mountainous terrain packed with ancient craters. This is entirely different from the moon's near side, which includes large circular basins formed by asteroid impacts. Those basins are obvious on the near side because they are places where darker colored lava from the moon's interior broke through and flooded the surface. But the far side crust is much thicker, which apparently prevented lava from reaching the surface. With its careful measurements of the moon's gravity, Grail can see deeper into the lunar interior and help shed light on why the moon's crust is so lopsided. It may even shed light on a surprising theory based on computer simulations that suggests the moon's thicker far side crust was created in a collision with a second smaller moon. This epic crash would have splattered material all over the far side, like a giant bug hitting a windshield. But there are also deeper questions to answer, including whether the moon has now lost all of its internal heat, or whether deep down it still harbors a small molten core. To probe the moon to such depth requires data from all angles. It takes the moon 1 month to rotate slowly on its axis. So after 3 months of orbiting the moon from pole to pole, Grail gathered enough data to map the moon's entire gravitational field in exquisite detail 3 times over.
Scientists are now continuing to analyze the treasure trove of data that Grail has provided, hoping for a definitive glimpse of the moon's mysterious heart. This is the promise of gravity as a tool for space exploration. It offers a way for us not just to see other worlds, but to feel what's happening inside them.
Not even Isaac Newton could have dreamed of such power. A power that can also help us reach beyond the solar system and explore the cosmos in an entirely new way. For more than half a century, conquering space meant conquering gravity. Gravity was the obstacle that had to be overcome in order to leave our planet behind and travel to the moon and beyond. But even then, scientists knew there was another way to think about gravity, not as a barrier, but as a messenger that can carry information from the distant universe. This idea comes from Albert Einstein. Unlike Newton, who thought of gravity as a force between objects, like an invisible bond, Einstein reimagined gravity as a curve or warp in space. The warp is created by matter, and it also dictates how matter moves. Take Earth, for example. Because it contains a lot of matter, Earth stretches and bends the space around it, forming a kind of dimple in 3 dimensions. As the moon moves, it's guided by the way the space around Earth is curved. Instead of traveling in a straight line, the moon's path follows the curve and keeps circling around us.
But this elegant way of thinking about gravity also has an interesting side effect. If space can stretch and bend, then space can also ripple like a wave, a gravitational wave. According to Einstein, space is full of gravitational waves, like ripples on a pond, created whenever something with mass accelerates. But in practice, these waves are so slight that we don't notice them in everyday life, and we have no means of measuring them as they propagate through space. That is, unless the situation is extreme. And in our universe, there is no situation more extreme than that of a black hole. A black hole is an object with gravity so strong that not even light can escape. Yet even though black holes give off no light, their effect on the space around them can be strong enough to generate gravitational waves. The key is looking for places where black holes are accelerating through space and making big ripples as they go. One such place could be the center of a massive galaxy. It's now thought that most galaxies have giant black holes in their core. Such a black hole may start small, but as it is fed by the galaxy that surrounds it, it can grow to the mass of 1 billion suns. And brightest galaxies in the universe are thought to have originally formed out of the collisions and mergers of smaller galaxies. If so, such galaxies could host not one, but 2 giant black holes locked in tight orbits around each other. Those orbits will eventually lose energy from decay, the black holes are locked in a death spiral, destined to collide. Drawn in by their mutual attraction, the 2 giants whip around each other at high speed. As they do, they generate massive ripples in space. Traveling outward, those waves will eventually sweep through our solar system, carrying information that could help scientists better understand the origin and development of giant black holes and their role in the history of the universe. But how to detect them? The answer is simply to measure space. Scientists have now begun to develop a measuring tool that will use lasers to detect minute changes in length across different distances in space. It's called LISA, the Laser Interferometer Space Antenna. LISA will consist of 3 spacecraft precisely spaced in a triangle that is 5 million kilometers to a side. Using laser beams to track their relative positions, they can detect a change in their separation down to 5 trillionths of a centimeter. Such extraordinary precision lies at the very limits of current technology. But it should be just enough to allow scientists to listen in on a universe that is filled with gravitational waves. What will it be like to perceive the universe? Most of the time, scientists expect it will be like listening to a continuous buzz, made up of waves from millions of black hole pairs located in galaxies scattered in every direction. But every now and then,
there should be a much larger boom of gravitational waves created whenever two black holes finally collide and merge. It's beyond the ability of even the world's most powerful telescopes to witness such an extreme and violent event. But Lisa could give us a front row seat.
Gravitational wave astronomy is so new that in a sense it hasn't even been born. That won't happen until a gravitational wave detector picks up its first real signal. But many researchers expect that moment is coming soon and that our generation will be the first to tune in to a whole new way of perceiving the universe.
As we do, we will again come face to face with a remarkable truth about our universe. Though it often appears vast and incomprehensible to the human mind, contained within its awesome beauty are the clues that will help us understand what makes the universe the way it is. A place where creatures like us can exist and explore. Traveling for hundreds of thousands of miles per day, yet always in sight of home. The product of a bold past, but also the bridge to an ambitious future. Designed to make spaceflight routine, it has taught us our most painful lessons about the danger that lurks whenever humans journey beyond our home planet. This is the legacy of the Space Shuttle, a vehicle that for over 3 decades came to define human spaceflight, while helping to create a permanent presence in orbit. But for scientists, the fleet of space shuttles also meant something more. They were traveling laboratories with access to the unique environment and perspective of low Earth orbit. Impossible to reproduce on the ground, this was to be the setting where astronaut researchers would test the limits of materials, the universe, and even their own bodies. All essential information that could one day help humans venture much farther into deep space. Of the 5 shuttles that blasted off from Cape Canaveral, only 3 remained. But despite the tragic loss of Challenger and Columbia, the program successfully completed 133 missions. And nearly 150 astronauts have flown in a shuttle, many of them making several trips.
The space shuttle may have completed its final journey, but over 30 years, it's managed to transform spaceflight by making it just a bit more routine, even as it's taught us that extreme exploration still comes with tremendous risks. The shuttle has also blazed a trail for science in space, a trail that continues aboard the International Space Station. Today, the idea of a continuous presence in space in support of scientific research
is no longer a dream. But it took the shuttle program to get there, and that took an act of true vision. In 1916, the same year that Neil Armstrong first walked on the moon, a small group of engineers in the California desert had a job to do. It was to build a vehicle to ferry people back and forth to low Earth orbit. Known as STS, the Space Transportation System, this new kind of spaceship wasn't going nearly as far. And to be affordable, it would have to be reusable, a space plane that could survive both liftoff and re-entry. These early test models were dubbed flying bathtubs because of their clunky shape. But what they lacked in grace, they made up for in stamina. Designed to deflect heat away from the crew cabin, the vehicle's wide underbelly was the key that would allow it to endure the searing, high-speed descent through the atmosphere over and over again. The final shuttle design included wings for stability, a feature that would allow the craft not just to descend, but to glide into a low-impact landing. The design was flight tested by releasing the shuttle from the back of a specially outfitted Boeing 747. But no flight test on Earth could reproduce the harsh environment of space. So, on April 12, 1981, the first of the shuttles to be readied for orbit sat poised on the launch pad.
6, 5, 4, we've gone for main engine start.
And as Columbia soared successfully into the sky, a 30-year journey for science on the shuttle was set to begin. With better access to space than ever before, researchers had a long list of topics they were eager to explore with NASA's new orbiter. And the first subject of serious studies in the space shuttle was the one that was visible just outside the crew cabin window, Earth. By now, views of our planet from a few hundred kilometers up were a familiar sight, thanks to earlier chapters of the space program. But with bigger windows than the space capsules of the 60s and 70s, and with better technology to take advantage of that view, the shuttle raised Earth observations to a new level. This effort was already underway by the second space shuttle mission, which carried an imaging radar, a way of bouncing microwaves off of Earth's landform to build up a detailed picture of our planet's diverse geography. The radar system proved to be a powerful tool for Earth scientists, because unlike photography from space, it worked regardless of whether it was imaging the day or the night side of the planet. It was also unaffected by cloud cover. Flying aboard the shuttle 3 times over the next 13 years, the radar system returned alluring and spectacularly colorful views of the surface. For scientists eager to study our world from above, there was no doubt the space shuttle had arrived, and it was showing them Earth like they'd never seen it before. It's said that beauty is only skin deep. But when it comes to imaging Earth from orbit, being able to see beneath the skin is a big advantage. That was the principle behind the space shuttle's imaging radar, which not only bounced microwaves off the planet's surface, but watched them penetrate a little way into the surface, allowing the system to see hidden information in the underlying rock and soil. Here, for example, a spectacular view of Mount Etna on the island of Sicily, one of the world's most active volcanoes. It reveals the complex succession of lava flows that have spilled down the mountain sides over many generations. Scientists compare images like these with what they observe on the ground and can use them to help explore more remote volcanoes from orbit. In another case, the dry, blowing sands of the Sahara Desert nearly conceal this curious geologic feature lying just below the surface. But because radar can penetrate the top layers of sand, this shuttle radar image of the Arunga crater in northern Chad shows...
Acne spot? Banish the blemish with an emergency spot patch from Curology, now at Target.
The twice as nice guarantee. Not satisfied? Get your money back and more.
It's not a sale. It's an Aldi thing.
Shows what happened when a small asteroid collided with Earth hundreds of millions of years ago. The shuttle was used to study the possibility that the asteroid broke up into pieces before it struck, leaving not one crater, but a chain of at least 3 craters. Elsewhere, the same technology has also helped document more immediate changes. Here we see a shuttle radar view of Chile's vast and remote Patagonia ice field, taken in October of 1994. In this view, red and purple indicate areas of high elevation. By comparing this image to one taken in the same shuttle mission, researchers were able to measure the speed at which different parts of the glacier are moving. Such measurements are crucial for understanding how Earth's icy regions are responding to global climate change.
We've gone for main engine start.
By the year 2000, the use of the Space Shuttle as a radar platform had evolved into the Shuttle Radar Photography Mission, which produced high-resolution elevation data for 80% of Earth's surface. The result was, at that time, the most detailed map of our world ever made. The Space Shuttle also explored our home planet in other ways. On 3 missions between 1992 and 1994, it carried the Atlas experiment, designed to measure the chemistry of Earth's atmosphere and its interactions with the Sun. Among its many contributions were data that support the realization that chlorofluorocarbons, or CFCs, are damaging Earth's protective ozone layer, and that their production had to be curtailed. But this was just the beginning. Throughout the 1980s and 90s, the Space Shuttle offered a gateway for science in space of all kinds, especially science that could take advantage of the most obvious feature of space travel: the fact that in orbit, the concept of up and down seems to vanish.
The reason things behave so differently in low Earth orbit is also what makes it difficult for humans to work there: microgravity. As the shuttle orbits, it's actually falling around the Earth. Everything in it is falling too. The gravity is still there, but its effects are no longer felt. This microgravity environment affects every aspect of spaceflight, from the design of the toilets to the way we might expect to grow plants for food in the future.
Without gravity as a guide, plants have no sense of down. Roots sometimes grow in the same direction as leaves.
The effects of microgravity extend even to the smallest scale. In one startling shuttle experiment, salmonella bacteria were shown to become more active in space. Working with the space bacteria, scientists were able to identify the gene that switches on this behavior, a possible step toward developing a protective vaccine against salmonella, one of the most common causes of food poisoning. But humans are also not immune to the effects of spaceflight. In perpetual freefall, the gravitational cues that the body relies on for everything from muscle development to circulation to perception are gone. And while the sensation of flying in space can be liberating, at the physiological level, microgravity presents a severe challenge to the human body. One of many that must be surmounted before humans can live permanently in space. The space shuttle has been crucial to building up our understanding of what happens to the body when it's in space. But perhaps most important of all, starting in the late 1990s, the space shuttle became the essential tool for creating the International Space Station. A more ambitious and longer-lasting presence in space, and a stepping stone into the future. And with human spaceflight reaching for new heights, so too were the scientists eager to make use of the new facility to extend human knowledge into new frontiers. From the moment the first space shuttle took flight, humanity was on a new path. One that made low Earth orbit a familiar destination for an entire generation of astronauts. But the shuttle was, first and foremost, a vehicle, not a port. Even the longest shuttle missions were rarely over 2 weeks. Of low Earth orbit from many types of experiments, researchers needed a permanent laboratory rather than an occasional visit. So, to establish a new outpost in space for a new century, NASA, the U.S. Space Agency, teamed up with Russia, Europe, Japan, and Canada to create the International Space Station, one of the boldest construction projects in history. Of course, the shuttle would play a key role in building the station. Starting in 1998, it began ferrying up many of the modules and other elements needed for the giant habitat. In combination with the pieces lofted up by Russian Proton and Soyuz rockets, the massive station gradually began to take shape, reaching its completion only with the final few shuttle flights some 13 years later. During those years, the space shuttle became less available to scientists eager to pursue experiments in orbit. But the end result was something far grander and more versatile. By November of 2000, astronauts began arriving for the first long-duration missions to the station. The station has been occupied ever since, setting a new record for continuous human presence in space. In its current form, the space station accommodates 6 astronauts, giving researchers an unprecedented platform from which to conduct experiments in life sciences, materials science, earth science, and astronomy. And with a construction cost nearing $100 billion, NASA and the other partners behind the station are eager to get the most benefit possible out of the facility. In May of 2011, during what would be the second-last space shuttle mission, astronauts delivered a final piece of scientific apparatus to the station. An unusual detector designed to probe some of the most powerful and mysterious energy sources in the universe. It's called the Alpha Magnetic Spectrometer 2.
I'm Jerry. I smoked, and I have late-stage COPD.
2, a device that counts and measures the high-speed particles coming from all directions in space, known as cosmic rays. It's thought the most powerful cosmic rays are generated by supernova explosions and giant black holes. To even more exotic processes at work in the cosmos. The trick is seeing enough of them to spot the types of cosmic rays that are truly rare. The vast majority of these particles are ordinary cosmic rays that are already well understood by scientists. But a very few of them will carry hints of an exciting discovery, possibly revealing whether other parts of the universe are made of antimatter, or else helping to identify the nature of the darkness that astronomers suspect is everywhere around us and completely invisible to ordinary telescopes. In more practical terms, the AMS-2 will give scientists their best information yet about the high-energy particle environment in our solar system. This knowledge is crucial for understanding how astronauts may one day avoid the hard radiation exposure that is one of the main hazards of a long interplanetary voyage.
Having fired the imagination of a generation, its place in history secure, the space shuttle pulls into port for the last time.
Following the final flight of the space shuttle in July of 2011, a new chapter was opened for the International Space Station. One in which private spacecraft, like the Dragon capsule built by SpaceX, take up some of the work of bringing supplies to the station. With private companies servicing the space station, the hope is that NASA can move on to more challenging destinations, like taking humans back to the moon, or the asteroids, or Mars. Meanwhile, the International Space Station will continue to provide a platform for science in space. Some wonder if the station has been worth all of the trouble and expense to build, but its true legacy may be in setting the stage for a longer-term human presence in the solar system.
Oh, this is fantastic. Looks nice. Nice.
stark desolation or breathtaking beauty. The planet Mars offers both at once and much more. No other world has so captivated human imagination, and apart from Earth, no other planet has been more closely examined or studied. Yet Mars continues to defy our expectations. And the closer we look, the more we realize we barely know Mars at all. The act of exploring another world is a plunge into the unknown. But Mars is different. So many spacecraft have been sent there that by now its major features are as familiar to scientists as the continents of the Earth. Today, the real unknowns on Mars are found at a smaller scale, a human scale. And exploring them takes a keen eye for detail. Today, there's no keener eye on Mars than the one that belongs to MRO, the Mars Reconnaissance Orbit. Like a great bird scanning for prey, MRO soars over Mars with its solar panels outstretched, using the most powerful camera ever sent to another world to peer down at the alien terrain passing below. As it orbits from pole to pole, MRO scans the surface, creating images in long strips that are only a few kilometers wide, but could stretch to well over 100 kilometers long. Within these narrow strips, MRO's sensitive camera can perceive features as small as a dinner plate. That's many times sharper than any previous spacecraft has ever seen Mars from orbit. And it means that MRO is the first orbiter with the power to connect the Mars we see from space with the Mars we wish to explore on the surface. False color images that are chosen to bring out interesting features, MRO's views of Mars are views at the level of local geography. But taken together, the small-scale details they reveal help to tell a very big story, both about the planet's current conditions and the ancient processes that produced this astonishing landscape. And because those processes involve heat and water, it is also possible that billions of years ago, they enabled the emergence of life on Mars. If life once did gain a foothold here, the evidence is buried under layers of Martian rock, layers that MRO can discern better than any other orbiting spacecraft. In fact, MRO has turned Mars into a planet of land, allowing scientists to explore Martian history as though it were the skin of a giant onion. MRO has also shown Mars to be a planet salted by wind, where fine-grained dust can form vast fields of dunes that gradually migrate across the planet. The dunes of Mars are spectacular, rippled masterpieces that remind us of nature's power to create and destroy entire landscapes one sand grain at a time. With their shifting, sinuous features, the dunes bring Mars to life, revealing the dynamic nature of its surface. But the wind can also create phenomena that are much more fleeting. In many regions of Mars, MRO has found dark streaks crossing the plains, like scribble marks from a giant pen.
These are the tracks left by dust devils, wispy whirlwinds that traipse across the surface like miniature tornadoes, scouring the rocks clean of dust as they go. Dust devils are so common on Mars that MRO has captured several of them. Here, one twists serpent-like above the plane, casting a long shadow that reveals the dust devil is nearly a kilometer high. Elsewhere, there is a different kind of evidence that Mars can be the scene of dramatic action. Here, the spacecraft examines a crater that was not present in its 2009 photo, but appeared in 2011. In false color, the freshly excavated debris of the blast looks bright blue against the dusky surface. These fresh impacts are not just curiosities. The material they expose provides clues to what lies just below the Martian surface. And sometimes they can even expose a hidden layer of ice, the frozen remains of Mars's warmer, watery past. MRO has also seen plenty of ice sitting on the surface of Mars, but this is dry ice, made up of frozen carbon dioxide rather than frozen water. As it comes and goes with the seasons, the dry ice can take on a fascinating diversity of forms, sometimes appearing as though painted on the Martian surface by an artist with a flair for the improbable. And sometimes the view of a Martian polar terrain covered with dry ice can even seem to resemble bacteria under a powerful microscope. So powerful is the eagle eye of MRO that it has even been used as a telescope to look up at the two moons of Mars, Phobos and Deimos, as they orbit high overhead. These moons may someday serve as outposts, where human astronauts arrive before descending to explore interesting sights on the planet below. By then, the surface of Mars will have been scattered and sampled by a new generation of robot explorers, and those robots will be looking to MRO to tell them where to land. On the smooth slopes of Pavonis Mons, a giant Martian volcano, the Mars Reconnaissance Orbiter makes a startling discovery. Small craters below on the featureless landscape appears to have a strangely dark center. Looking more closely, MRO finds that what seems like a crater is really a natural skyline, where part of a volcanic formation has collapsed, exposing a hidden cave below. This remarkable picture invites the tantalizing prospect of someday entering the cave and exploring Mars beneath the surface. But falling into such a hole unexpectedly would spell disaster for a rover on Mars. And that's why orbiting missions are used to spot both the hazards and the opportunities on the bright planet.
When it comes to Mars, every orbiting spacecraft has two jobs. The first is to explore the entire planet from above, gathering the clues that researchers need to put together the story of the red planet on a global scale. The second job is to pave the way for exploration on the surface of Mars by finding the perfect place to land. With its high-powered view of the surface, MRO has played a key role in the planning of missions to land on Mars, offering more information about potential landing sites than once was ever thought possible. In the history of Mars exploration, this is still a recent development. In fact, two of the best-known Mars explorers, NASA's Spirit and Opportunity rovers, had already been working on the surface for years before MRO arrived. Amazingly, MRO's vision is sharp enough to spot the rovers on the surface, although each is not much larger than a wheelbarrow. Here, the orbiter zooms in on the rover's Spirit, which gleams brightly as sunlight reflects off its solar panels. Meanwhile, over on the other side of Mars, MRO finds Opportunity perched on the rim of Endeavour crater. With a diameter of 22 kilometers, this is the largest feature Opportunity has explored to date. It headed this way after MRO saw evidence for minerals related to water in its orbital view of the crater. Soon after MRO reached Mars in 2006, it had its first assignment helping a surface mission find the best landing site. The mission was Phoenix, a lander designed to touch down in the north polar regions of Mars and probe for the permafrost believed to lie just below the surface. Prior to MRO's arrival, mission planners favored an area known as Region B for Phoenix's landing site. But with their improved view from MRO, they found that Region B was full of boulders that would have spelled disaster had the lander set down on one. Instead, a backup landing site was chosen, and Phoenix landed safely in May of 2008. Soon after, MRO was able to confirm the lander's position by imaging it from space. For the first time in history, a landing on Mars had come with its own eyewitness. The next mission to Mars was to be much more complicated. Instead of a lander, NASA had decided to send another rover to follow up on Spirit and Opportunity's impressive finds. This newer and much larger rover was to be the most sophisticated probe ever to set down on Mars, an entire mobile laboratory. And it might be the first to determine if Mars once had conditions suitable for life. And with only one rover to land, there would be no second chances. MRO set about scouring the planet, helping pinpoint geologically interesting locations. As with earlier missions, high priority was given to places where there is evidence for past water flowing on the surface of Mars. Starting with a list of more than 60 candidate landing sites, scientists began a detailed 5-year investigation to find the best possible location for the next rover on Mars. Using data from all available orbiter missions, but relying especially on detailed views from MRO, scientists managed to narrow the list to 4 finalist sites by the spring of 2011. Among them were some of the most intriguing and geologically complex places on Mars. Places such as Holden Crater, an ancient formation that was turned into a vast lake when a channel carrying floodwaters breached the crater rim. Just north of Holden is another candidate site, Eberswald Crater. It also shows signs of past flooding,
But here, the key feature is an ancient river delta at one end of the crater. A very different kind of landing site presents itself at Mars Vallis. Billions of years ago, this channel drained a torrent of water from the Martian highlands in the south to the low-lying northern plains. All three of these sites show terrific potential for uncovering the history of water on Mars. But in the end, scientists chose a fourth site, a site that combines some of the most attractive features of all the others in one location, and adds a mysterious mountain that could unlock the secrets of ancient Mars. After more than 40 years of interplanetary exploration, Mars has offered some of the most spectacular sights in the solar system. From huge volcanoes, to deep chasms, to the beautifully sculpted layers of ice and dust that cover the Martian poles. But among its many diverse and intriguing features, there is nothing on Mars that looks quite like this. A giant mound, more than half the height of Mount Everest, sitting squarely in the middle of an ancient impact crater. This is Gale Crater, a formation that has long attracted interest and speculation from Mars scientists. It's also the landing site of the most ambitious mission ever to touch down on the Red Planet, NASA's Mars Science Laboratory, better known as the Curiosity rover. Compared to previous rovers, Curiosity is built like a tank. The size of a small car, it weighs 900 kilos and carries 10 separate scientific instruments for the detailed testing of the rocks, soil, and atmosphere of Mars. But most importantly, Curiosity is powered by a device that generates electricity from the radioactive decay of plutonium. Curiosity's nuclear power supply will give it the potential to explore Mars for years, allowing scientists to select a more ambitious target. And few features on Mars are as scientifically interesting. This strange formation rises above everything else around it. over 1,400 kilometers per hour and just 11 kilometers from the surface, Curiosity deployed its parachute. It fell away, revealing the rover tucked inside. But now, the rover was still falling fast when it separated from its parachute and back shell and ignited 4 powerful descent rockets. But how exactly to land? Separating from its descent stage, the rover was lowered to the surface on 3 nylon cables. As it touched down, the cables were cut and the descent stage veered off, crashing to the surface a safe distance away. And then came the signal.
Curiosity is the 7th mission to land successfully on Mars, but it's different from all its predecessors in a crucial way. It is the first Mars mission to combine the mobility of a rover and the scale and complexity of a field laboratory with the potential for operating for years on the planet's surface. That combination will change our understanding of Mars forever.
This will be the longest journey ever attempted on another world, but it will not be as lonely. As Curiosity begins its epic trek across the surface, it will be watched from above by MRO, the eagle eye that has become part of day-to-day life on Mars, even as we look for signs of life in the past.